Hello there, and welcome to the Sleepy Science Documentary Podcast. Tonight we'll be exploring the profound mystery of rogue planets, those solitary wanderers that drift through the void of space without any star to orbit or call their own. These are worlds that were either born alone from collapsing clouds of gas and dust, or were once part of a thriving planetary system before violent gravitational encounters tore them away from their stars and cast them into isolation. The rogue planets drift through darkness. These quiet wanderers move through the cold emptiness between stars, untethered and unlit by any sun. They exist in perpetual night, never knowing the warmth of radiation from a stellar companion. Each one is a mystery, a story written in rock and ice, in gravity and solitude. We'll discover rogue planets that have traveled across light years of tippy space, that carry secrets from their origins, that might harbor strange life in the depths of their atmospheres, or beneath crusts of ancient ice. From worlds as small as Earth to giants larger than Jupiter, rogue planets reveal the slow and quiet forces that shape galaxies far beyond what we once thought possible. If you enjoy these quiet journeys into the cosmos, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one curious soul at a time. But for now, just breathe. Allow your mind to drift away into the vast expanse. Let the gentle pull of imagination settle your thoughts. Let us begin. Rogue planets drift in darkness without stellar anchors, existing in isolation that defines their nature. These worlds orbit nothing, floating through the void as solitary objects in endless darkness. Unlike planets bound to the sun, rogue planets have been cut loose by chaotic encounters and wander forever alone. No day breaks on a rogue planet. No sunrise illuminates a horizon. No light warms the atmosphere or soil. There is only darkness, profound and endless, broken by the distant light of other stars too far away to matter. In this darkness, these worlds continue their patient journeys, moving through space at velocities determined by gravity and the momentum from ejection. They are among the most alien worlds, existing in conditions so extreme they challenge our understanding of how worlds might persist for billions of years without stellar energy. Some rogue planets formed normally before violent ejection from their parent systems. These worlds started as dust and rock accumulating in protoplanetary disks around newborn stars, growing through collisions into planetary bodies. For millions of years they may have orbited peacefully, experiencing regular day-night cycles like Earth. Then came chaos, dynamical instability inevitable in multi-planet systems. Close encounters trigger gravitational scattering, where mutual perturbations alter orbits dramatically. A single gravitational interaction can accelerate a planet to escape velocity, giving it enough energy to overcome the star's pull forever. The world finds itself cast outward, traveling away forever. Some rogues were ejected by stellar encounters, passing stars strong enough to fling planetary members into the void. These ejected worlds carry memories of their origins, chemical compositions, and internal heat, reflecting their formation around distant stars they will never see again. Detection methods rely on gravitational microlensing events, where rogue planets are revealed not by light they emit, but by their effects on distant starlight. As a rogue planet drifts through space, and passes in front of a background star. Its gravity bends the starlight in a phenomenon predicted by Einstein's relativity. The planet acts as a lens, magnifying the star's light, creating characteristic brightening that astronomers detect. This brightening is temporary, lasting hours to days depending on the planet's mass. The smaller the rogue planet, the briefer the event. Astronomers monitor millions of stars watching for these signals. The signal might brighten a star by 20% for hours, yet that flicker holds enormous significance. Modern micro-lensing surveys use automated systems flagging candidate events. The technique is elegant and effective, allowing detection of invisible objects, though limitations have recently been overcome using multiple telescopes simultaneously in space and on Earth. Rogue planets may outnumber stars in the galaxy, fundamentally reshaping our understanding of worlds populating the cosmos. Recent estimates suggest approximately 2 trillion rogue planets drift through the Milky Way, potentially exceeding visible stars. Some researchers propose even more extreme ratios, suggesting between 100 and 100,000 rogues per star, totaling around a quadrillion wanderers. This means most planets in the universe are not orbiting stars but floating alone between stellar systems. Planets are far more abundant than imagined, with formation occurring through independent processes in interstellar clouds. A planet like Earth orbiting the Sun bathed in stellar radiation represents one of the rarest worlds in existence. Most worlds are cold, dark, isolated, ancient, and alone. The universe is populated primarily by lonely wandering worlds rather than star-bound planets, transforming our perspective on planetary science. Internal heat can sustain warmth for billions of years in rogue planets. When a planet forms, it inherits thermal energy from gravitational processes. This primordial heat remains trapped deep within the interior, contained by insulating rock and ice layers. Additionally, rogue planets benefit from radioactive decay of heavy elements like uranium and thorium, which releases energy continuously over geological timescales. This is the same process keeping Earth's interior warm billions of years after formation. For rogue planets without external stellar energy, this internal heat becomes extraordinarily precious, the only warmth against space's crushing cold. A massive rogue planet, perhaps Jupiter-sized, could maintain temperatures hundreds of degrees above the interstellar background for incredibly long periods. The larger the planet, the longer it retains heat, as thermal energy is trapped deeper and heat escape is proportionally smaller. Ancient rogue planets could still possess significant internal heat driving geological processes within their depths. Atmospheric pressure could maintain liquid water without sunlight, suggesting rogue planets might harbor surprising chemical complexity. Theoretical models propose a thick, hydrogen-rich atmosphere traps infrared radiation from the planet's warm interior, creating a greenhouse effect, raising surface temperatures significantly. This far-infrared opacity is maintained by atmospheric density, pressure trapping heat, attempting to escape. In such conditions, water on a rogue planet's surface might remain liquid rather than freezing, not from stellar energy, but from internal heat and atmospheric pressure raising the boiling point. A rogue planet with such an atmosphere and sufficient internal heat might maintain liquid water, creating a potentially habitable environment radically different from Earth. Water would exist in darkness, warmed from below by geological heat. Some rogue planets might possess oceans, vast bodies of liquid water in perpetual darkness, cycling through thermal convection and chemical reactions needing no sunlight. Jupiter-sized rogues create their own magnetic fields, generating magnetospheres, extending thousands of kilometers and shielding interiors from cosmic radiation. A massive rogue planet possessing gas and liquid metallic hydrogen contains a core where electrical currents generate magnetic fields through electromagnetic principles, creating dipoles potentially much stronger than Earth's magnetosphere, depending on mass and rotation. The field could protect the atmosphere from cosmic rays and solar wind. Magnetospheres trap charged particles, creating regions similar to Jupiter's Van Allen belts, where particles spiral along field lines. These belts might produce auroras if atmospheric gases are present, charged particles colliding with molecules to produce light. A strong magnetic field suggests a molten interior, indicating significant internal heat-generating motion in the planet's depths. Rotation rate directly influences magnetic field strength. The combination of magnetic fields and atmospheric particles creates a dynamic environment unique to rogue planets, a protected bubble in an otherwise harsh void. Some rogues travel at incredible velocities through space, ejected with force moving at tens or hundreds of kilometers per second relative to galactic medium. Velocity depends on gravitational dynamics, how close the rogue came to other planets before final encounters. Some were ejected gently, gaining only a few kilometers per second. Others received tremendous kicks, accelerating them to traverse entire galaxies in tens of millions of years. A high-velocity rogue planet experiences ram pressure from interstellar medium passage. Even negligible density creates measurable pressure, compressing the leading hemisphere and creating a bow shock like a ship's bow wave. This shock heats the atmosphere and ionizes gases, creating luminous wakes. Heat can warm the leading side, potentially allowing liquid water in localized regions briefly. Over millions of years, gravitational interactions slow these travelers as trajectories curve through the galaxy's field, eventually settling into slower velocities and peaceful wandering. Brown dwarfs blur the line between planet and star, occupying ambiguous space, challenging fundamental distinctions. The dividing line is set at 13 times Jupiter's mass, the threshold for deuterium fusion in cores, marking brown dwarfs rather than planets. Below this, objects lack central pressure for fusion and remain planets. Above, nuclear reactions sustain, and the object is a brown dwarf. This distinction is somewhat arbitrary, based on specific processes rather than fundamental differences in formation or appearance. Many rogue objects exist at this boundary, and determining whether they are massive planets or low-mass brown dwarfs requires precise measurements. Some rogue planets initiated deuterium fusion, making them technically brown dwarfs, while others formed through planetary rather than stellar processes. Evidence suggests some objects classified as brown dwarfs formed in protoplanetary disks through planet formation before ejection. These ambiguous objects exist in twilight zones between categories, demonstrating the universe does not always fit neatly into understanding boxes. Ejection events leave gravitational signatures in natal systems, allowing astronomers to infer rogue planet presence. When planets are ejected through gravitational scattering, They leave altered orbits of remaining planets telling stories of past violence. Orbital resonances and spacing reveal where rogues once resided and their former masses. Computer simulations show particular planet arrangements carry imprints of ejection events, with surviving planets occupying configurations reflecting dynamical history. Widely separated orbits suggest massive planet ejections, while tightly packed systems suggest gentle ejections. Some systems possess highly eccentric or inclined orbits, stable only if massive objects were recently ejected. Unusual debris belt structures hint at past ejection events with gaps or asymmetries indicating departed companions. Astronomers use these signatures, estimating how many rogues were ejected and their masses. Remaining planets become witnesses to violence, producing rogue planets now wandering the galaxy. Rogue planets can capture moons during their wandering, acquiring satellites through gravitational encounters with drifting objects. In sparse interstellar medium, collisions are vanishingly small, but gravitational capture is possible with correct geometry and velocities. A rogue planet might encounter free-floating moons ejected from systems or asteroids from distant origins. With correct speeds and angles, smaller objects are drawn into gravitational orbits around the rogue, becoming moons despite the primary lacking a star. Captured moons might be old, having orbited other stars for billions of years. A rogue with moons becomes a miniature system, worlds orbiting in darkness experiencing tidal forces despite absent parent stars. Moon presence affects geology and habitability as tidal heating supplements planetary internal heat. Multiple moons interact gravitationally, creating complex orbital dynamics and collisions. These systems show loneliest worlds build satellites, creating multi-body systems functioning without stars. Ancient rogues may predate our solar system's formation, existing since the galaxy's earliest epochs. Some rogues were ejected during chaotic early planetary system formation, in the first tens of millions of years when dynamical instability was most pronounced. Such ancient worlds traveled through the galaxy for billions of years before our Sun condensed. These represent the oldest planetary objects, their surfaces bearing marks of incomprehensible ages. An ancient rogue ejected billions of years ago saw countless stars come and go, passing within light years of systems, occasionally perturbing moons or asteroids but never captured. Internal heat cooled over billions of years, yet radioactive elements in cores continue decay, providing steady warmth. Surfaces are heavily cratered, marked by impacts from long wandering. These worlds carry information about the early galaxy, their compositions reflecting element abundances from cosmic time's earliest epochs. Finding ancient rogues provides insights into galaxy and planetary system formation. Dense atmospheres trap residual formation heat, creating insulating blankets, slowing rogue planet cooling and maintaining higher temperatures. Thick atmospheres composed of hydrogen and helium, the universe's most abundant elements, have density and pressure-absorbing and reabsorbing infrared radiation from warm planetary interiors. Far infrared opacity creates greenhouse effects without sunlight, trapping internal radiation. Denser atmospheres more effectively trap heat, potentially maintaining liquid water temperatures despite absent external heat. Molecular composition matters, hydrogen having strong infrared opacity characteristics making excellent insulators. Early-stage rogue planets might have very thick atmospheres inherited from formation, gradually lost through thermal escape as molecules gain escape velocity energy. Over billions of years, slow atmosphere loss extends heat retention periods, allowing planets to remain warm longer. Initial conditions at formation or ejection directly influence thermal evolution across billions of years of solitary wandering. Some rogues glow faintly in infrared wavelengths, emitting thermal radiation revealing their presence. Young rogue planets freshly ejected or recently formed carry creation heat, appearing bright in infrared. Modern telescopes like James Webb detect these signatures, identifying hundreds of candidate rogues in star-forming regions. Thermal radiation comes from planetary surfaces and atmospheres. Warm outer layers radiating accumulated interior heat or trapped greenhouse effects. As rogues age, they cool gradually, infrared signatures dimming. Very old rogues become invisible in infrared, cooling to near ambient interstellar temperatures. Distinction between young and old rogues becomes clear through infrared. Bright young ones easily detected, while ancient ones become extraordinarily difficult. Infrared glow serves as a clock, brightness indicating approximate age and thermal history. Bright rogues were ejected millions of years ago, while barely detectable ones wandered darkness for billions of years. Binary rogue planets orbit each other in darkness, pairs bound by mutual gravity without external influence. Binary systems form when rogues gravitationally capture others, or when planets are ejected together remaining bound. In binary systems, two planets orbit their common center of mass, sometimes with hierarchical relationships like Earth-Moon systems in interstellar isolation. Dynamics are fascinating. Tidal forces between worlds potentially generating significant heat and geological activity. Close orbits create considerable heating, maintaining subsurface oceans or geological activity longer than solitary rogues. Orbital periods depend entirely on masses and separation, with no external forces disrupting relationships. These systems are stable, persisting indefinitely. Binary rogues demonstrate planets are not isolated individuals, but can form small societies, multiple worlds creating miniature systems functioning without stellar companions. Collision events between rogues reshape planetary bodies, potentially creating moons and altering topography dramatically. In sparse interstellar medium, collisions are extraordinarily rare, but with billions of years and trillions of rogues, they occur occasionally. Collisions release tremendous energy, kinetic impact converted into heat, and gravitational energy. Depending on velocities and masses, impacts might be gentle, leaving planets intact, or violent, vaporizing objects. Less violent collisions fragment impact areas, creating new moons from debris. Gentle encounters result in coalescence, two objects merging into single larger worlds through gravitational attraction. Merged rogues experience enormous heating, potentially liquefying interiors, establishing intense geological activity. Survivors possess unusual geology, with impact melts and features reflecting collisions creating them. These rare events represent dramatic transformations in rogue planet lives. Radioactive decay generates sustained internal energy, providing primary heat, maintaining rogue planets for billions of years. Heavy elements like uranium, thorium, and potassium contain unstable isotopes decaying, transforming and releasing energy. This energy from planetary cores gradually diffuses outward, creating steady heat flows. Radioactive heating amounts depend on element abundance and formation history. Metal-rich stars' disk material contains more radioactive elements than primordial clouds, retaining heat longer. Radioactive decay rates gradually decrease following predictable exponential decline, with isotope-specific half-lives. Despite gradual cooling, radioactive heating remains significant in ancient rogues. Heat drives mantle convection, transporting heat from depths outward. This is the same process keeping Earth's interior warm, driving plate tectonics. For rogues, radioactive heating represents energy lifelines in cold, dark universes. Tidal forces from captured moons provide additional heating through frictional processes, extending geological activity periods. When rogues capture moons settling into stable orbits, gravitational interactions pull on planetary mass, creating bulges and deformations, flexing solid or liquid interiors. Tidal forces do mechanical work, friction converting work into heat. Heating intensity depends on moon mass, distance, rogue rigidity, and orbital properties. Large, close moons create dramatic forces and significant heating comparable to radioactive decay. Small, distant moons create negligible heating. Tidal heating maintains subsurface oceans in liquid states, even on low-heat rogues, friction continuously pumping energy. Moon presence becomes extraordinarily significant for long-term habitability and geological activity. Some rogues with captured moons experience dramatic tidal heating phases where geological activity reaches extraordinary levels. Ice shells may cover subsurface oceans on water-rich rogues, creating layered structures with frozen crusts protecting liquid water. Rogue planets with significant water content and sufficient internal heat develop such structures naturally. Surfaces are covered in ice kilometers thick, insulated from frigid interstellar medium by thermal properties. Beneath shells, liquid water circulates, potentially forming global oceans, driven by internal heat and tidal forces from moons. Ice-water boundaries create chemical complexity interfaces where energy flows and gradients support chemical or biological processes. Cracks allow water percolating upward, creating cryovolcanic features, spewing water or slush. Ice-covered oceans represent intriguing habitats for exotic life, environments with liquid water and energy despite interstellar darkness. Ice shells protect from cosmic radiation, allowing subsurface life avoiding destructive cosmic rays. These ice-ocean worlds might represent the most common environment where liquid water persists on rogues. Rogue planets pass through molecular clouds gathering material, slowly accumulating gas and dust through denser interstellar regions. Interstellar medium contains areas of higher density where molecular clouds concentrate gas and dust far exceeding average. When rogues' trajectories carry them through clouds, they encounter thicker mediums beginning material accumulation through gravitational capture. Dust particles and gas molecules are drawn into planetary wells, adhering to surfaces or absorbing into atmospheres. Over millions of years traversing clouds, rogues accumulate significant material, gaining noticeable mass. This process is slow and gentle compared to violent collisions, continuous and inexorable. Accumulated material consists of simple cloud molecules including hydrogen, helium, water ice, and organic compounds, adding surface layers and atmosphere thickness. Extended cloud periods make rogues gradually less pure, acquiring material from different clouds, developing compositional histories reflecting journeys. Accumulation rates depend on cloud density and planet speed. Slower planets accumulating more material. Some rogues repeatedly pass through clouds during lifetimes, experiencing faster growth, alternating with slower periods. Gravitational interactions slow or accelerate rogues, with star encounters and massive objects altering trajectories. As rogues drift through galaxies, they occasionally pass near stars or encounter massive objects, including other rogues, stellar remnants like neutron stars or black holes, or dark matter concentrations. Encounters involve gravitational interactions altering velocity and direction, bending paths through space. Interaction details depend on specific geometry and masses, fundamentally transferring momentum between objects. Close massive star encounters could slow rogues substantially, capturing worlds into orbits or reducing speeds through gravitational braking. Conversely, compact objects like black holes accelerate rogues dramatically, flinging them at greater speeds. Multi-play lifetime encounters gradually reshape galaxy trajectories, potentially altering velocities significantly. Some rogues encountered numerous stars, accumulating small changes resulting in dramatic redirections. Rogue trajectories evolve over cosmic timescales, shaped by accumulated gravitational influences from everything encountered. Magnetic fields protect some rogues from cosmic radiation, shielding atmospheres and surfaces from high-energy particles. Rogue planets with strong magnetic fields generated by internal dynamos create magnetospheres extending into surrounding interstellar medium, trapping deflecting charged particles. Cosmic rays, primarily high-energy protons but including heavier elements and electrons, bombard galaxies traveling at near-light speeds, capable of penetrating matter and damaging molecular structures including DNA. Without protective magnetospheres, cosmic rays penetrate atmospheres, potentially reaching surfaces, creating harsh radiation. Magnetospheres function as shields, using field lines redirecting charged particles, preventing lower atmosphere and surface reaches. Protection strength depends on field strength, stronger fields providing better protection. Small rocky worlds lacking magnetic fields experience unshielded cosmic radiation exposure, profoundly affecting surface life. Magnetic protection becomes increasingly important for rogues lacking nearby stars, providing stellar wind shielding. Large rogue magnetospheres serve as crucial buffers against cosmic environment harshness, determining habitability. Chemical reactions in thick atmospheres create complex molecules despite sunlight absence. Internal heat providing energy, building intricate structures. Rogue atmospheres, particularly thick hydrogen-rich envelopes, are not inert, but active chemistry sites where molecules collide, react, forming compounds. Energy sources include thermal interior energy, cosmic rays penetrating upper atmospheres, and radioactive element decay in atmospheres. Without sunlight, no photochemistry occurs, no visible or ultraviolet-driven reactions, but heat and high-energy particles drive reactions. Complex organic molecules, life precursors, form through such chemistry building from simpler components. Stellar UV radiation absence might protect molecules from photodissociation, allowing accumulation rather than breakdown. Some atmospheres contain rich chemical libraries featuring thousands of different molecular species. Chemical reactions continue throughout atmospheres, modified by temperature and density gradients, creating chemical gradients and dynamic material exchange. Complex chemical systems represent chemistry pushed to unfamiliar extremes. Primordial heat persists longest in massive rogue bodies, largest planets maintaining thermal energy while smaller ones cool. Planetary cooling depends on size, larger objects cooling slower, possessing more thermal mass and lower surface area to volume ratios. Heat diffuses outward from hot interiors toward cool surfaces at rates depending on surface area and temperature gradients. Doubling planetary radius increases volume eightfold, multiplying heat-producing mass by 8 while increasing surface area fourfold. Massive rogues cool extraordinarily slowly, retaining thermal energy for timescales comparable to universe ages. Jupiter-sized rogues might retain thousands of degrees central temperatures billions of years after formation. Earth-sized rogues cool more rapidly, potentially dropping to near ambient temperatures within billions of years. Distinctions between large and small become pronounced in long-term thermal evolution. Large rogues remain warm and geologically active, maintaining favorable exotic chemistry or life conditions. Small rogues cool more rapidly, potentially becoming inert and uniform temperature throughout. Rogue planets temporarily orbit galactic structures including spiral density waves and the galactic bar, shifting orbital characteristics periodically. Galaxies are not static but dynamic systems containing spiral arms defined by density waves rotating at distinct velocities. Rogues passing through galactic environments experience gravitational forces from combined star and gas cloud masses creating large-scale structures. Rogues entering spiral arms experience enhanced gravity, temporarily trapped in tighter orbits before drifting out. The galactic bar, large-scale rotating structures in many galaxies including the Milky Way, creates gravitational variations influencing rogue orbits. Some rogues spend extended periods in resonant orbits with these structures, orbital parameters locked in specific rotation rate relationships. This creates orbital stability for extended periods, potentially lasting millions of years before rogues break free. Interaction with galactic structures means rogues do not follow simple trajectories, but experience gradual shifts and oscillations, navigating complex galactic gravitational landscapes. Orbital variations expose rogues to varying interstellar medium densities or occasional star proximity. Some rogues retain ring systems from their stellar past, possessing belts of debris orbiting in the equatorial plane, remnants of captured or accreted material. A rogue planet that was violently ejected from its birthplace might retain some of the debris disk that once surrounded it, debris too widely distributed to be reaccreted quickly but gravitationally bound to the planet. These rings would persist over billions of years, gradually spreading outward as tidal interactions gradually transfer angular momentum to the outer portions of the disk. The rings would consist of fragments ranging from microscopic dust grains to bodies kilometers in diameter, all orbiting in synchronization with the planet's rotation. Such rings are not unique to rogue planets. Jupiter and Saturn in our solar system possess ring systems, as likely do many exoplanets, but rogue planet rings occupy a unique niche as the most isolated ring systems in the universe, orbiting worlds that receive no light from stars and thus remain invisible except through subtle gravitational effects. The presence of rings indicates a history of capture or debris, a memory of formation processes or encounters. The ring particles, like any other component of a rogue planet system, gradually lose orbital energy through collisions and eventually spiral into the planet's atmosphere or impact the surface. But this process unfolds over timescales of billions of years, making rings a persistent feature of rogue planets possessing them. The rings would create shadows and patterns in any hypothetical magnetosphere, altering how charged particles are distributed. Aurora displays occur on magnetized rogues without stars, created when charged particles accelerated by magnetic field processes collide with atmospheric gases and produce light. A rogue planet with a strong magnetic field and a substantial atmosphere possesses all the ingredients necessary for auroras, just like the auroras that occur on Earth, Jupiter, and other planets. The driving force for auroras comes from the interaction between the planet's magnetic field and external forces, including cosmic wind and galactic magnetic field interactions. Charged particles spiral along magnetic field lines, accelerating and gaining energy, eventually colliding with atmospheric molecules. These collisions transfer energy to the molecules, exciting electrons to higher energy states, and when the electrons return to lower states, they release photons of light. Different atmospheric gases emit different colors, creating displays with reds, greens, blues, and other hues depending on the composition. For a rogue planet, these auroras would occur in the perpetual darkness with no competing stellar light to overwhelm them, creating brilliant displays sometimes extending across hundreds of kilometers of the sky. The auroras would vary in intensity and frequency, responding to fluctuations in the external cosmic wind and magnetic field interactions. A persistent, though slowly changing, display of light would grace the night sky of any hypothetical observer on the rogue planet's surface, a visual manifestation of the electromagnetic drama occurring in the planet's magnetosphere. These auroras would be among the most remarkable and beautiful natural phenomena in the universe, rivaled by few other displays in their scale and brilliance. Ancient impacts created massive scars on wandering surfaces, with craters accumulating from billions of years of exposure to the cosmic environment and its occasional catastrophic collisions. As a rogue planet wanders through the galaxy for billions of years, it inevitably encounters many small objects, including asteroids, comets, and meteorites traveling through space. Each impact leaves a scar, a crater marking the point of collision, recording in stone the history of encounters. Very ancient rogue planets would be heavily cratered, their surfaces bearing the accumulated marks of an incomprehensibly long history of impacts. The sizes of impact craters range from microscopic to enormous, depending on the sizes of the impacting bodies. A collision with a large asteroid might create a crate hundreds of kilometers across, shattering rock and excavating vast quantities of material. The largest impacts could create surface features visible across enormous distances, mountains and depressions that dominate the landscape. The ejector from large impacts would scatter across the surface, creating surrounding regions of disrupted terrain and sometimes small secondary craters from impact debris. The rate of impacts would have fluctuated throughout the rogue planet's history, with periods of enhanced impacts when the planet passed through particularly dense regions of interstellar medium or debris-rich areas of the galaxy. The accumulated scarring would tell the story of the planet's journey, with impact densities potentially varying across different regions depending on the planet's trajectory through different environments. These impact scars are the visible record of a rogue planet's long history. Cryovolcanism erupts on ice-covered rogue worlds, with subsurface water or other volatile liquids penetrating through cracks in the frozen crust and erupting onto the frozen surface. Cryovolcanism represents one of the most exotic geological processes occurring on worlds where the dominant substance is ice rather than hot lava. On a rogue planet with a subsurface ocean beneath an ice shell, the internal heat rising from below can create pressure that forces water upward through weaknesses in the overlying ice. When water reaches the surface through a cryovolcanic vent, the extreme cold causes it to freeze rapidly, accumulating into distinctive formations quite unlike anything on Earth. A cryovolcanic eruption on a rogue planet might be subtle, merely a slow seeping of water and dissolved materials through a crack, or it might be explosive, a violent geyser driven by internal pressure. The material erupted would consist of water and dissolved salts or other compounds present in the subsurface ocean, creating deposits that gradually accumulate around the vent. Over millions of years, repeated cryovolcanic activity at a single location could build mountains of frozen material, with the composition reflecting the chemistry of the subsurface ocean. Cryovolcanism provides a mechanism for exchanging materials between the subsurface ocean and the surface, potentially importing chemical compounds from the warm depths to the frozen exterior. These cryovolcanic systems might support unique niches for life, if life exists on rogue planets, where warm water meets frozen ice and complex chemistry occurs at the interface. The cryovolcanic features visible on a rogue planet's surface would be among the most distinctive markers of its internal activity, standing as monuments to the geological drama occurring within. Rogue planets preserve records of their formation environments in the chemical compositions locked within their cores and icy mantles. When a rogue was ejected from its native system, it carried a signature of where it was born, chemical elements reflecting the star it orbited. Scientists studying rogue planet compositions can deduce their origins by analyzing isotope ratios and mineral associations unique to specific stellar environments. An unusually high abundance of heavy elements might indicate formation around a metal-rich star, while organic compound distributions reveal formation in complex chemistry regions. These planetary fossils tell stories of vanished systems and distant stars that no longer have planets, records written in stone from origins now separated by vast distances. Thick hydrogen atmospheres insulate super-Earth rogues, creating layers of gas that trap internal heat and prevent rapid cooling despite cosmic isolation. A super-Earth, perhaps 2 to 3 times Earth's mass, might possess a substantial hydrogen-helium envelope inherited from its formation in a dense protoplanetary disk. This thick atmosphere creates an insulating blanket where thermal radiation from the warm interior cannot easily escape, establishing a greenhouse effect operating without any sunlight. Pressure at the base of such atmospheres would be enormous, raising the boiling point of water and other volatiles sufficiently that subsurface oceans could remain liquid indefinitely. The atmospheric density would gradually decrease with altitude, creating temperature gradients where the uppermost layers experience frigid temperatures while lower layers remain warm. This stratification creates chemical gradients and dynamic circulation patterns moving heat and material throughout the atmospheric envelope, establishing complex atmospheric systems far more sophisticated than static models suggest. Some rogues were born in isolation without stellar nurseries, forming directly from collapsing gas clouds in interstellar space. The theory of isolated rogue planet formation proposes that planetary mass objects can condense from interstellar gas clouds through the same gravitational collapse processes creating brown dwarfs, but failing to accumulate sufficient mass for deuterium fusion. These independently formed rogues never experienced childhood in protoplanetary disks, never knew stellar radiation or stellar companions. Instead, they formed in darkness, accreting material from vast clouds of gas and dust between stellar populations. Their chemical composition reflects cloud chemistry rather than solar disk chemistry, containing unusual isotope ratios and element abundances differing from planets formed around stars. These wanderers represent the universe's most truly solitary objects, born alone and traveling alone through billions of years of cosmic existence. Galactic tidal forces influence rogue orbital paths, subtly warping trajectories over millions of years as rogues experience gravity from distributed matter across the galaxy. The gravitational field generated by the Milky Way's billions of stars, massive dark matter halo, and concentrated galactic center creates a complex landscape where rogue planets navigate slowly changing gravitational gradients. A rogue's path through this field is never perfectly straight, but curves continuously under the accumulated gravitational influence of everything around it. Close approaches to massive structures like stellar clusters or giant molecular clouds create detectable perturbations, nudging rogue trajectories by subtle amounts. Over timescales of millions of years, these accumulated small perturbations become significant, gradually reshaping orbital parameters and potentially redirecting rogues toward or away from regions containing stars or interstellar clouds. The galactic tidal environment acts like a slow-moving current, carrying rogues along paths determined by immense gravitational structures operating across light-year distances. Capture events briefly reunite rogues with stellar systems, allowing them to occasionally enter orbits around distant stars before escaping back into the void. When a rogue's trajectory carries it through a planetary system, its gravity can interact with existing planets, exchanging momentum and altering both the rogue's path and the system's internal structure. In rare cases, a rogue might be captured temporarily into a wide orbit around a star, becoming a planet for tens of thousands of years before gravitational perturbations eject it again. During this temporary capture, the rogue experiences stellar radiation for the first time, warming its surface and potentially activating dormant atmospheric chemistry. The reunion is always brief on cosmic timescales, lasting mere moments before the rogue gains escape velocity and continues its solitary journey. These temporary captures represent fleeting chances for rogues to experience stellar companionship experiences that reset their thermal clocks and leave subtle marks on surfaces. Subsurface chemistry could support extremophile life forms adapted to darkness and chemical gradients, creatures thriving in environments radically different from anything on Earth. Within rogue planets possessing subsurface oceans, chemical interactions between warm rocky interiors and cold water create gradients driving complex reactions. Mineral-rich water seeping upward from the rocky mantle meets cold descending water, establishing cycles of chemical exchange and energy flows. Dissolved minerals from planetary interiors create chemical gradients that organisms might exploit for energy, similar to how hydrothermal vent ecosystems on Earth operate without sunlight. Exotic organisms might develop metabolisms based on unusual chemistry, consuming minerals, hydrogen, methane, or other compounds abundant in subsurface environments. The diversity of potential biochemistries operating in rogue planet oceans might exceed the diversity of Earth's biosphere, as chemical richness persists indefinitely without photosynthetic constraints. Such ecosystems would be invisible to conventional astronomy, hidden within planetary interiors, and detectable only through subtle gravitational or thermal signatures revealing their presence. Rogue planets cross interstellar distances over millennia, traveling between stars at velocities measured in tens of kilometers per second. A rogue ejected with a velocity of 20 kilometers per second would traverse 1 light-year every 15,000 years, crossing star systems in time frames ancient compared to human history, but trivial compared to cosmic ages. Some rogues travel at much higher velocities, ejected violently from chaotic planetary systems. The intervening space between stars remains far emptier than any laboratory vacuum, offering minimal resistance to rogue motion. These lonely journeys continue inexorably, rogues moving through darkness toward destinations determined by velocities imparted billions of years ago. Occasionally a rogue passes close to a star, experiencing gravitational deflection, but rarely achieving capture. Most rogues' journeys involve passing through empty space, encountering no stars, colliding with nothing, experiencing only gradual cooling from radioactive decay. Gravitational lensing reveals hidden rogue populations, with massive rogues bending starlight sufficiently to alert astronomers to their presence despite emitting no light. Every massive object distorts space-time, and this distortion bends light rays traveling through warped space, a phenomenon Einstein predicted and astronomers later confirmed. Rogue planets with masses comparable to Jupiter create lensing effects observable when their gravity magnifies light from distant background stars, creating characteristic brightening patterns astronomers recognize. The brightness changes occur only when rogues pass almost directly between Earth and background stars, making each lensing event a rare alignment requiring patient observation of millions of stars. Each detected event provides information about the lensing object's mass and approximate distance, building a census of rogue populations through accumulated observations. Statistical analysis of these lensing events reveals rogue planet abundances far exceeding earlier estimates, suggesting populations numbering in the trillions throughout the galaxy. The technique transforms rogues from invisible ghosts to countable members of the galactic population, revealing worlds that would otherwise remain forever unknown. Some rogues orbit the galactic center in vast ellipses, following elongated trajectories carrying them from the crowded central region toward the sparse galactic disk, and back again over hundreds of millions of years. The galactic center contains immense stellar densities and gravitational influences from the supermassive black hole ruling that region, creating conditions where only extreme orbits remain stable. Rogues trapped in the galactic center's gravitational well follow orbits with periods measured in hundreds of millions of years. Enormous ellipses carrying them alternately closer to and farther from the dense central region. During close approaches to the galactic center, rogues experience intense tidal forces and frequent gravitational interactions with other objects, potentially undergoing dramatic orbital changes. During apocenter passages, rogues venture into the calmer disk regions, where stellar densities decrease and encounters become rarer. These vast orbital cycles expose rogues to dramatically varying environments, alternating between regions of high stellar density, where close encounters occur frequently, and sparse regions where rogues drift for millions of years encountering no thing. Temperature gradients create atmospheric circulation patterns on rogues with substantial atmospheres, establishing winds and weather systems driven purely by internal heat rather than stellar energy. A thick atmosphere surrounding a rogue with warm interior would experience temperature variations between the warm interior heated equatorial regions and cooler polar areas, creating pressure gradients driving winds. The circulation patterns would resemble terrestrial weather systems, but with different driving mechanisms, pure planetary rotation and heat distribution without stellar forcing. Atmospheric columns at equator and poles would exchange heat through circulation, establishing Hadley cell-like circulation patterns that transport thermal energy toward polar regions. Wind speeds might reach hundreds of meters per second, driven by steep temperature gradients between interior heated and cooler regions. Lightning could occur in regions where rising warm air carries moisture, encountering upper atmosphere layers cold enough to trigger condensation. The atmosphere would roil with dynamic activity, despite being utterly invisible. Perpetual storms churning within darkness. Rogue planets carry ejection velocity signatures in their motion through space, allowing astronomers to estimate how violently planets were ejected from their native systems. The velocity at which a rogue escapes its parent system reveals something about the nature of its ejection, whether it was a gentle dynamical instability or a violent chaotic encounter. Rogues ejected with low velocities might have originated in systems disrupted by mild instabilities, where planets gradually scattered each other over millions of years. Rogues traveling at extremely high velocities, sometimes hundreds of kilometers per second, were likely ejected catastrophically through close encounters with binary stars or massive third planets. The rogue's current velocity preserved the momentum imparted during ejection, serving as a fossil record of ancient dynamical events. By measuring velocities of large rogue populations and comparing them to theoretical predictions from simulations of planetary ejection, astronomers gain insight into how frequently chaotic planetary instabilities occur and how violent these events typically become. Each ejected rogue carries within its motion a message about the violence or gentleness of its birth. As an interstellar wanderer, close encounters with stars perturb rogue trajectories, with gravitational interactions deflecting rogues from their original paths, even when stars do not achieve capture. A rogue planet passing within a few astronomical units of a star experiences gravitational forces pulling it toward the stellar body, bending its trajectory slightly. The amount of deflection depends on the rogue's velocity, the star's mass, and the distance of closest approach, with faster rogues deflecting less and slower rogues bending more dramatically. Some rogues pass so close to stars that they experience temporary heating, warming their outer layers through radiation and gravitational friction. The encounter might trigger atmospheric responses, slight increases in wind speeds, or localized weather patterns in the outer atmosphere. Some rogues pass close enough to have moons stripped away by tidal forces, losing captured companions to the star's gravity. Multiple star encounters throughout a rogue's lifetime accumulate, gradually redirecting it through the galaxy in directions different from its original trajectory after ejection. These encounters represent dramatic moments in otherwise placid interstellar journeys, brief interactions with stellar radiation and gravitational forces before returning to dark emptiness. Mini-Neptune rogues retain thick, volatile envelopes inherited from their formation, possessing atmospheres of hydrogen, helium, water vapor, and complex organic molecules. A mini-Neptune, perhaps 5 to 10 times Earth's mass, forms in the dense inner regions of protoplanetary disks, where substantial hydrogen and helium still remain available. When such a rogue is ejected from its system, it carries this thick atmosphere into interstellar space, retaining volatile substances that would escape from smaller planets. The atmospheric composition would be layered, with denser, heavier molecules concentrated at the bottom and lighter hydrogen enriched toward the top, creating chemical stratification. Water vapor in the atmosphere would condense at higher altitudes where temperatures drop sufficiently, creating clouds of ice crystals floating in hydrogen atmosphere. The pressure at depth would be enormous, creating conditions where exotic phases of matter might exert compressed states of ordinary substances under pressures never experienced on terrestrial planets. These mini-Neptune rogues represent preserved samples of planetary formation materials, fossils of protoplanetary disk chemistry locked in atmospheric form. Internal convection distributes heat throughout rogue interiors, with hot material rising from the core while cooler material descends, establishing circulation patterns transporting thermal energy throughout planetary volumes. The process resembles Earth's mantle convection, where heat rises in plumes and descends in sheets, but continues indefinitely on rogues without external cooling from a stellar wind or radiation. Convection patterns would be influenced by the rogue's rotation rate, with faster rotation creating Coriolis effects that organize convection into cells and columns. The core regions would remain hottest, while boundary layers adjacent to the icy crust would be cooler, establishing temperature gradients driving continued convection. Convective motions would stir the interior, distributing radioactive elements that decay and generate heat, ensuring heat production occurs throughout the volume, rather than concentrating only at the core. The convection patterns would evolve over billions of years as the rogue cools gradually, with internal circulation patterns changing as temperature contrasts decrease. These invisible convection systems represent the only activity occurring within cold dark rogues, silent geological machinery, operating forever hidden from observation. Some rogues spin rapidly from formation angular momentum, rotating around their axis with periods of just a few hours despite lacking external torques. A rogue's rotation rate depends partly on the angular momentum present during its formation or ejection, with certain formation scenarios producing rapidly spinning worlds. Rapid rotation creates centrifugal effects that modify the shape of a rogue, causing equatorial bulges similar to those visible on rapidly spinning stars. The rotation also influences magnetic field generation, with faster spinning core regions creating stronger dynamos producing more powerful magnetospheres. For rogue planets possessing atmospheres, rapid rotation would create pronounced Coriolis effects, organizing atmospheric circulation into distinct latitude bands where winds rotate in different directions. A rogue with a 10-hour rotation period would spin faster than Jupiter, creating dramatic centrifugal forces that compete with gravity. Over billions of years, tidal interactions with captured moons could gradually slow rotation, gradually reducing spin rates as rotational energy transfers to orbital energy. Ancient rogues might have slowed substantially from their formation spin rates, now rotating with periods measured in days rather than hours. Cosmic ray bombardment alters surface chemistry over time, with high-energy particles penetrating planetary atmospheres and crust, creating novel chemical compounds and occasionally damaging complex structures. Unshielded by stellar wind, rogue planets experience unfiltered cosmic ray exposure, creating radiation-driven chemistry in their outer layers. Cosmic rays, primarily high-energy protons but including heavier nuclei and secondary particles, penetrate matter, creating ionization cascades that break molecular bonds and recombine atoms into unexpected configurations. The surface chemistry would gradually evolve as radiation-driven reactions accumulate, transforming initial composition into secondary products rich in free radicals and exotic compounds. Complex organic molecules produced by chemical reactions in rogue atmospheres would be gradually destroyed by cosmic ray impacts, limiting their accumulation. However, molecules constantly reform through ongoing chemistry, establishing an equilibrium between creation and destruction. Cosmic rays penetrating into subsurface layers would ionize molecules and alter crystal structures in surface rocks, gradually transforming surface geology over billions of years. The radiation effects would be strongest near magnetic poles, where cosmic ray focusing concentrates particle streams, potentially creating distinct chemical regions with differing compositions. Rogue planets may host chemosynthetic ecosystems, with life forms deriving energy from chemical reactions rather than sunlight, thriving in subsurface oceans and hydrothermal systems. On Earth, Hydrothermal vents support chemosynthetic ecosystems powered by energy released when hot mineral-rich water meets cold water, driving oxidation-reduction reactions. Rogue planets with warm interiors would possess similar conditions, supporting chemosynthesis at interfaces between warm and cool water. Organisms adapted to darkness and high pressure might exploit chemical gradients between oxygen-rich upper layers and hydrogen-rich deep regions or methane-producing vents. Some hypothetical rogue organisms might metabolize hydrogen directly, using hydrogen abundance as an energy source. The abundance of chemical energy could support complex ecosystems with diverse trophic levels, food chains extending from chemosynthetic producers through predatory consumers. Such ecosystems would be invisible to external observation, hidden within planetary depths, potentially thriving for billions of years unknown to the universe beyond their dark prison. Stellar flybys occasionally strip atmospheric layers from rogues, with close passages to stars creating heating sufficient to drive atmospheric escape. When a rogue passes close to a star, intense radiation heats the upper atmosphere significantly, warming molecules to velocities exceeding escape speed. The stellar radiation ionizes atmospheric molecules, creating charged particles in magnetic fields that can be swept away by stellar wind. The amount of atmospheric loss depends on the rogue's approach distance and the star's radiation intensity, with very close approaches potentially removing substantial atmospheric layers. A rogue experiencing multiple stellar flybys throughout its existence might lose significant mass, gradually becoming stripped of atmospheres that took millions of years to form. The process would be most dramatic for small rogues with low surface gravity, insufficient to retain heated gases, while massive rogues could weather numerous close approaches while preserving most of their atmospheres. Some rogues might be reduced from mini-Neptune status to super-Earth status by repeated stellar encounters, their composition transformed by loss of volatile layers. These stripping events represent catastrophic moments in rogue existences, brief violent interactions, leaving permanent marks on planetary structure. Ice giant rogues preserve exotic ice phases deep within their interiors, with pressures so extreme that water and other volatiles exist in states unknown at surface conditions. An ice giant rogue possesses layers where pressure increases tremendously with depth, creating conditions where water exists as superionic ice, a form solid as rock but flowing internally as a liquid. Beneath superionic ice layers might exist metallic water compressed so intensely that electrons delocalize from atoms, creating liquid states with metallic properties. Such exotic phases would be unique to rogue planets and the most extreme planets around stars. Conditions so extreme that they barely exist elsewhere in the universe. The physics of these exotic states governs heat transport and internal convection patterns differently than ordinary ice or water. The transition between different ice phases would create boundary layers affecting how heat flows through the interior. The very existence of these exotic states on rogues makes them natural laboratories for studying matter under extreme conditions. Specimens of physics operating at extremes rarely encountered anywhere in the universe. Multiple ejection events send planets on complex paths through the galaxy, with some worlds experiencing multiple dynamical instabilities that eject them repeatedly from different systems. A planet ejected from one system might be captured by another system, orbit for millions of years, then be ejected again by subsequent instabilities. Each ejection would impart additional velocity, potentially accelerating the rogue to higher speeds than achieved through a single ejection. A rogue experiencing multiple ejections might travel at velocities greater than what any single system's dynamics could produce, creating extreme wanderers traveling faster than almost all other rogues. Such objects would have traveled incredibly great distances by the present era, potentially having journeyed through multiple galactic regions. The chemical composition of multiply ejected rogues would contain contributions from multiple systems, creating worlds with mixed chemistry from different stellar environments. Their trajectories through the galaxy would be extremely complex, with multiple deflections and redirections creating paths totally different from simple straight-line extrapolation of initial ejection velocity. These complex wanderers represent rogues that experience the most eventful histories. Worlds touched by multiple planetary systems before becoming permanent wanderers. Rogue planets accumulate interstellar dust over eons, gradually gaining mass from encounters with sparse dust floating between stars. The interstellar medium contains not just gas, but also dust particles, microscopic grains of silicates, carbon compounds, and ice created through processes occurring in ancient stellar atmospheres and supernova. As rogues wander through regions of higher dust density, particularly within molecular clouds, they accumulate these particles through gravitational capture. The dust particles stick to surfaces or are incorporated into atmospheres, gradually adding mass to the rogue. Over billions of years of continuous accumulation, even from extremely sparse interstellar dust, a rogue can gain measurable mass. The accumulation rate would be highest during periods when rogues pass through dense molecular clouds, and nearly zero during passages through empty interstellar space. Some rogues might have accumulated enough mass to noticeably change their composition, acquiring a coating of interstellar material distinct from their original planetary surface. The accumulated dust would carry isotopic signatures, revealing its origins in ancient stellar processes, potentially preserving evidence of supernovae and stellar evolution occurring billions of years ago. Thermal emission fades as primordial heat dissipates, with rogue planets gradually cooling across cosmic timescales and infrared signatures dimming as surface temperatures approach the interstellar background. A rogue ejected recently remains warm from its formation and ejection, radiating infrared light detected by telescopes sensitive to thermal emission. As millions of years pass, the thermal energy gradually escapes into space, causing surface temperatures to drop slowly. The infrared radiation decreases as temperatures fall, making old rogues progressively harder to detect through infrared observations. Eventually, after billions of years, even massive rogues cool to temperatures approaching the interstellar medium's ambient 2.7 Kelvin, becoming invisible even to sensitive infrared detectors. The cooling process accelerates initially, but slows as rogues cool deeper, approaching asymptotically toward ambient temperature. Very young rogues detected through infrared glow were probably ejected millions of years ago, while ancient rogues, undetectable in infrared, were likely ejected billions of years ago during the galaxy's earliest epochs. The thermal history of rogues creates a timeline where older rogues are colder and fainter, while young rogues are warm and bright, allowing astronomers to age-date rogues through thermal measurements. Some rogues originated in disrupted stellar systems, worlds that were stable planetary members of thriving systems before gravitational chaos tore them free. These rogues might preserve memories of their former systems in orbital peculiarities or unusual compositions reflecting the specific stars they once orbited. A rogue that spent millions of years orbiting a metal-rich star would carry chemical signatures reflecting that origin, isotope ratios, different from planets formed around metal-poor stars. Some rogues might have been ejected at relatively recent times, astronomically speaking, thousands or millions of years ago, rather than billions, meaning they have not yet undergone extensive cooling and still possess surface conditions somewhat similar to their original systems. The ejection events that freed these worlds were likely violent, involving gravitational scattering that might have damaged their surfaces or volatilized surface materials. Surviving the chaos required substantial size and structural strength, suggesting most ejected rogues are substantial planets rather than small Earth-sized worlds. The disrupted systems that ejected these rogues might still exist, though now missing one or more members, and with remaining planets in altered orbits, reflecting the chaotic violence of ejection events. Captured satellites maintain elliptical orbits around rogues, with moons acquired through gravitational encounters following stable but elongated orbital paths. A moon captured by a passing rogue would enter an elliptical orbit where the distance to the rogue varies between perigee, closest approach, and apogee, farthest separation. The ellipticity of these orbits would depend on the orbital mechanics during the capture event, with different captures producing different eccentricities. The moon would experience tidal forces stronger during perigee when closest to the rogue and weaker during apogee passages. The combination of tidal heating and orbital dynamics would influence the moon's geology and surface evolution over time. Some moons might undergo substantial tidal heating, maintaining geological activity despite lacking internal radioactive heating. Multiple moons orbiting the same rogue would interact gravitationally, gradually altering orbital parameters through long-term perturbations. The orbital stability of captured moons would depend on moon masses and separation distances, with some configurations stable for billions of years and others gradually decaying as moons spiral inward. Atmospheric escape processes thin rogue envelopes gradually, with thermal escape and chemical-driven escape mechanisms slowly removing gases over geological timescales. Hydrogen and helium, being the lightest elements, escape most readily, with molecules gaining sufficient speed to exceed escape velocity through thermal energy. Heavier elements like oxygen and nitrogen escape more slowly, remaining bound for extended periods. Over billions of years, even massive rogue atmospheres would lose significant fractions of their original hydrogen content, gradually becoming richer in heavier elements as light gases preferentially escape. Chemical escape processes involving ions created by cosmic ray ionization can add additional escape mechanisms, creating charge separation that allows heavier elements to escape more readily. The escape rates depend on atmospheric temperature, composition, and magnetic field strength, with magnetic fields potentially reducing escape by containing charged particles. Ancient rogues might have retained only tiny fractions of their original atmospheres, now possessing dense atmospheres of heavy elements, while original hydrogen content has largely escaped. The process of gradual escape shapes rogue atmospheric evolution, transforming compositions over cosmic timescales toward increasing metal content and decreasing hydrogen. Rocky rogues cool faster than gas giant wanderers, losing internal heat more rapidly due to smaller size and higher surface area to volume ratios. An Earth-sized rogue, being much smaller than Jupiter, possesses much less thermal mass and higher surface area relative to its volume, allowing heat to escape more efficiently. Radioactive decay occurring throughout the rogue's volume provides ongoing heat generation, but smaller rogues radiate away heat faster than larger rogues generate it. Over billions of years, Earth-sized rogues might cool to near ambient temperatures, approaching thermal equilibrium with the interstellar background. Jupiter-sized rogues, being massive objects with low surface area to volume ratios, retain internal heat much longer, potentially maintaining temperatures hundreds of degrees above ambient after billions of years. The cooling differences mean that age-dating rogues requires accounting for size, with similar-aged young rogues of different sizes possessing dramatically different current temperatures. Some rocky rogues might be ancient beyond comprehension, having cooled to near interstellar background temperatures after wandering alone for tens of billions of years. The thermal contrast between giant and rocky rogues means that if both types exist in abundance, the universe contains both cold, dark, rocky worlds and warmer, massive planetary cores, maintaining persistent internal heat. Magnetic dynamos persist in metallic hydrogen layers, generating magnetic fields deep within gas giant rogues where pressure has compressed hydrogen into metallic states. Metallic hydrogen in planetary interiors contains mobile electrons, creating electrical currents capable of generating magnetic fields through dynamo processes. The moving metallic hydrogen layers in rotating planets create changing magnetic fields, inducing electrical currents that reinforce and sustain primary magnetic fields. The strength of the magnetic field depends on the size of the metallic hydrogen region, the rotation rate of the rogue, and the electrical conductivity of the material. Very old gas giant rogues that have cooled substantially might experience reduced dynamo efficiency as temperature drops and while conductivity changes. However, the dynamo process appears robust and persistent, maintaining magnetic fields indefinitely as long as the rogue remains rotating and possesses molten conducting interiors. Some rogues might possess planetary-scale magnetic fields comparable to Jupiter's magnetosphere, creating regions thousands of kilometers across, where charged particles are trapped and confined. The magnetic fields of rogues would interact with cosmic rays and the interstellar magnetic field, creating magnetospheres that protect atmospheres while deflecting cosmic wind from the sparse interstellar medium. Rogue planets experience seasons from axial tilt alone, with rotational axes inclined relative to orbital planes or galactic reference frames, creating variations in internal heat distribution, while rogues lack orbits around stars, eliminating traditional seasonal variations in stellar heating. Axial tilt creates seasonal effects through redistribution of internally generated heat. The tilt causes different planetary hemispheres to receive different amounts of internal heat transport based on rotation patterns and atmospheric circulation, creating temperature variations between equator and poles that shift with time. These variations would be subtle compared to stellar-driven seasons on Earth, but would create measurable temperature oscillations if rogues possess sensitive measuring instruments. Atmospheric circulation patterns would adapt to the slow seasonal shifts, creating dynamic weather patterns that wax and wane with planetary rotation. The timescale of these seasons would equal one rotation period, with some rogues experiencing rapid seasonal cycling every few hours if rotating quickly, or drawn-out seasons lasting days if rotating slowly. Over longer timescales, tidal interactions with captured moons might gradually alter axial tilt, creating slower variations in seasonal patterns. These internal seasons represent the only temporal variations in rogue conditions, the only way internal processes create cyclic oscillations. Ancient water ice sublimates in low-pressure environments, converting directly from solid to vapor when surface pressure drops below triple point values. A rogue planet that formed with surface water ice might experience gradual loss of that ice through sublimation as atmospheres thin and surface pressure decreases. Once atmospheric pressure drops below triple point values, water ice cannot exist as liquid and transitions directly to vapor when heated, even slightly by internal warmth or cosmic ray impacts. The loss of water ice exposes fresh rock beneath, creating new surface textures and chemical compositions as weathered surfaces are cleared away. Over billions of years, some rogues might lose essentially all surface water ice accumulated during formation, becoming dry rocky worlds entirely without volatiles on their surfaces. The water vapor lost through sublimation would eventually escape into space through the atmospheric loss mechanisms operating on all rogues. Some very ancient rogues might be desiccated worlds completely lacking surface water, their original volatile inventories lost to sublimation and escape across billions of years of wandering. The process creates distinct rogue types, young water-rich worlds, and ancient desiccated worlds representing different stages of volatile evolution. Gravitational focusing effects amplify background starlight, with massive rogues bending light rays and concentrating stellar radiation they encounter toward focused points on their far sides. While rogues receive no light from a primary star, they do encounter light from distant background stars passing nearby. When rogue gravity bends this light, some rays converge on the far side of the planet, creating regions where background stellar radiation becomes concentrated and amplified. The focusing effect is most pronounced for massive rogues with strong gravity and distant sources of light, potentially amplifying background starlight by factors of 2 or more in localized regions. The focused light would create hotspots on the far side of the rogue, regions where external radiation becomes sufficiently concentrated to warm the planet's surface. These hotspots would be transient, existing only when the rogue passes through fields of background radiation at proper angles. The phenomenon represents a subtle way that rogues interact with background radiation of the galaxy, weak amplification effects occurring regularly during long cosmic journeys. The focused radiation effects are too subtle to detect from Earth, but would be significant for any hypothetical observer existing on the rogue's surface, creating variable illumination from distant stars as rogues drift through the cosmic void atmosphere from the surface into space. The retention of hydrogen and helium in rogue planet atmospheres depends critically on gravitational strength and surface temperature, with heavier planets like super-Jupiters maintaining thick gaseous envelopes indefinitely, while smaller terrestrial rogues lose their atmospheres over billions of years. This distinction creates fundamentally different planetary types, some remaining as gas giants maintaining hydrogen atmospheres, while others strip down to bare rocky cores after cosmic ages of gradual escape. Rogue super-Jupiters create powerful magnetospheres, establishing regions where magnetic fields dominate the interstellar medium and deflect cosmic rays before reaching planetary surfaces. A super-Jupiter, with mass 10 times Jupiter's, possesses an enormous metallic hydrogen core generating magnetic fields through dynamo action. These fields extend hundreds of thousands of kilometers across, where magnetic force exceeds interstellar pressure. Cosmic rays striking these magnetospheres deflect around the system rather than penetrating directly to the surface. The deflection creates magnetotails extending downwind from the rogue's motion, wakes of deflected particles trailing behind. For rogues with captured satellites, these magnetospheres protect moons within the magnetic boundary from unfiltered cosmic ray exposure. Orbital resonances once governed now ejected planets. Mathematical relationships between orbital periods that influenced gravitational interactions before chaos scattered systems. When rogues orbited native stars, their motion was constrained by gravitational interactions, creating orbital resonances where adjacent planets maintained simple mathematical ratios. A resonance might mean that for every 2 orbits of an inner planet, an outer planet completed one orbit, creating gravitational beat patterns, influencing evolution. These resonances can be stable indefinitely or unstable, amplifying orbital eccentricities until planets scatter chaotically. Ejected rogues retained memory of these ancient dynamics in their trajectories, carrying angular momentum from resonant interactions. Astronomers studying rogue velocities can sometimes infer backward the resonance relationships that governed their motion, reconstructing structures of planetary systems long since scattered. Spacing between planets in intact systems often reflects resonance relationships, suggesting survivors avoided chaotic instabilities that ejected the rogues. Some rogues possess multiple moons in stable configurations, captured satellites orbiting in precise relationships where mutual gravitational perturbations balance persisting for billions of years. Rogues might capture multiple moons through individual encounter events scattered across cosmic journeys, each moon added through separate gravitational interactions. Collections of moons exist in orbital configurations determined by mutual gravity, with inner moons orbiting faster and outer moons more slowly. Orbital spacings reflect stability constraints, sufficiently separated to avoid chaotic interactions. Some configurations resemble Jupiter or Saturn systems, where multiple satellites coexist stably despite complexity. Over billions of years, tidal interactions gradually modify orbits, inner moons drifting inward while outer moons drift outward in gravitational exchange. Multiple moons transform solitary wanderers into miniature planetary systems containing multiple bodies orbiting central rogues. Differentiated interiors separate into distinct layers, with gravitational weight compressing planets into concentric shells of different material properties. The outermost crust is relatively cool where pressure remains low and rock behaves as rigid solid. Beneath lies the mantle, a hotter region where rock exists as plastic solid, capable of flowing over millions of years. Deeper still lies the outer core, where temperatures and pressures become extreme enough that iron flows like liquid. The innermost core remains solid, despite extreme heat, compressed so intensely by overlying weight that iron remains solid despite surface of sun temperatures. Gravity compresses planetary interiors with heavier elements sinking toward centers, while lighter materials float upward. Radioactive decay provides energy for continued differentiation as denser materials slowly sink toward cores. The layered structure creates distinct thermal gradients and chemical compositions shaping magnetic field generation and internal circulation patterns. Rogue planets witness galaxy evolution from dark isolation, observing galactic transformations across billions of years while drifting through cosmic voids. As rogues wander, they traverse regions that evolve dramatically, witnessing stellar populations change as massive stars died while smaller stars survived to old age. Rogues ejected early in galactic history observed mergers with other galaxies, gravitational interactions reshaping structures and triggering intense star formation. They continue wandering through altered galaxies, experiencing gradual quieting of star formation activity as galaxies aged. Ancient rogues ejected billions of years ago observed substantial changes in surrounding galactic environments, appearance of new stars, extinction of old ones, shifting patterns of cosmic structure. Rogues serve as silent witnesses to galactic history, unchanged themselves while universes around them evolved continuously. Their existence across eons records slow transformation of galaxies through unchanging presence, survivors of eras ancient beyond human comprehension. Thermal vents could warm localized surface regions, with geothermal activity driven by radiogenic heating creating hotspots where subsurface material reaches surfaces and releases thermal energy. Radioactive elements within rogue mantles decay continuously, releasing heat flowing upward through conductive rock. In regions where crusts contain thin patches or fractures, heat reaches surfaces more efficiently, creating localized hot regions where temperatures reach hundreds of Kelvin despite frigid interstellar environments. If rogues possessed subsurface water, thermal vents might create hot springs where warm water meets cold surface environments, establishing chemical gradients and temperature boundaries for exotic chemistry. Vents would be temporary geological features active as long as radioactive decay continues, but destined to fade as rogues cool over billions of years. Around thermal vents, specialized microorganisms might theoretically thrive, drawing energy from temperature and chemical gradients between warm subsurface and cold surface. Vents would represent only truly warm regions on otherwise frigid worlds, islands of heat where geothermal processes maintain temperatures far above interstellar backgrounds. Stellar encounters create temporary atmospheric disruptions, with close passages causing heating sufficient to trigger intense winds and alter chemical compositions. When rogues pass within astronomical units of stars, stellar radiation increases dramatically, warming outer atmospheres and increasing molecular velocity. Heating creates pressure gradients driving powerful winds accelerating to thousands of meters per second in outer atmospheres. Intense radiation ionizes molecules, breaking chemical bonds and creating charged particles interacting with magnetic fields. Upper atmospheres heat hundreds of degrees above normal, creating temporary hot layers that radiate energy away as rogues move from stars. Heating accelerates chemical reactions, recombining molecules into different configurations, creating temporary abundance variations. Once rogues pass beyond stellar influence and return to normal interstellar environments, atmospheres gradually cool and reactions reverse, restoring normal composition over weeks or months. Ancient lava flows solidified on cooling terrestrial rogues, preserving evidence of epochs when internal heat drove volcanism and created molten rocket surfaces. Terrestrial rogues formed recently within last few billion years possessed sufficient heat to drive widespread volcanism across rocky crusts. Massive eruptions released lava covering huge areas, creating layered deposits of cooled volcanic material. Over time, radioactive decay powering volcanism gradually declined, reducing heat flux through crusts and diminishing activity. Eventually, internal heat decreased sufficiently that volcanic activity ceased entirely, leaving dead worlds with ancient lava flows as only evidence of past activity. Chemical compositions of ancient flows reveal interior compositions and temperatures at which lava cooled, allowing reconstruction of conditions when rogues were geologically young. Some flows created unique surface features like shield volcanoes or calderas, topographic signatures of ancient volcanism persisting billions of years. Rogue planets follow galactic rotation curves, participating in overall rotation of the Milky Way despite not orbiting stars or being bound to specific galactic structures. The Milky Way rotates with different regions moving at different velocities depending on distance from galactic center and position within disk or halo. Rogues ejected from planetary systems inherit velocities of parent star systems, including orbital motion around galactic centers plus ejection velocity. As rogues travel through galaxies, they maintain velocities through empty space, neither speeding up nor slowing down absent strong gravitational deflection. Over cosmic timescales, trajectories relative to galactic centers remain consistent, allowing astronomers to determine origins by extrapolating backward. Rogues ejected from galactic disks might travel into galactic halos, regions far above or below dense stellar planes. Others might circle galactic centers, oscillating between regions of different stellar densities, as trajectories carry them alternately toward and away. Phosphorescent minerals glow faintly on rogue surfaces, with radioactive decay creating light detectable in complete darkness. Some minerals contain radioactive isotopes, like thorium and uranium, that decay, releasing energy as radiation and heat. When decays occur within crystalline minerals, energy excites electrons into higher states, with electrons releasing excess energy as visible light photons. This radioluminescence creates faint dark glows, allowing minerals to self-illuminate. On cold, dark rogue worlds, Such minerals create faint glows on surfaces where no sunlight illuminates. Glows are extremely faint, visible only to sensitive detectors, but represent only natural illumination on some surfaces. Over billions of years, as isotopes decay, brightness gradually decreases, a slow fading as minerals' radioactive content diminishes. In subsurface environments where organisms might evolve, faint phosphorescent glows could provide energy for photochemical reactions, driving unique biochemistries. Core crystallization releases latent heat over time, as liquid outer cores gradually solidify, transferring heat into surrounding mantles. Outer cores remain liquid due to extreme temperatures, but as rogues cool across billions of years, outer boundaries eventually cool sufficiently that iron and nickel crystallize from liquid to solid. Phase transitions release latent heat, energy stored in liquid material, released during crystallization. Latent heat flows outward into mantles, contributing to thermal budgets and temporarily slowing cooling rates as interiors release stored energy. Core crystallization is gradual, occurring slowly over billions of years. As boundaries advance inward, liquid-solid interfaces migrating towards centers. Eventually, outermost outer core layers crystallize, transforming to solid iron and nickel. Latent heat released extends periods during which rogues maintain internal heat, driving geochemical processes and potentially supporting subsurface life. Migrating rogues transport organic compounds between systems, carrying complex carbon-based molecules that seed life origins on distant worlds. During formation in protoplanetary disks, rogues accumulate organic compounds created through chemical reactions with ultraviolet light, water, and precursors. When ejected from systems, rogues carry accumulated organic inventory into interstellar space. Over millions of years, rogues encounter other stars and potentially pass close enough to capture planets or asteroids. Organic compounds could transfer to nearby bodies during close encounters, seeding worlds with chemical building blocks. Some compounds incorporate into planetary atmospheres or surfaces through accretion. Introducing carbon chemistry to worlds lacking such compounds, rogues serve as vectors for organic distribution across galaxies, suggesting life chemistry distributes widely between stars by wandering planetary bodies. Tidal heating maintains liquid layers on captured satellites, with gravitational interactions between massive rogues and orbiting moons creating stress-generating internal heat. Satellites orbiting rogues experience tidal forces that vary as moon distances change along elliptical orbits. As moons approach periapsis, tidal forces intensify and compress interiors. As moons recede toward apoapsis, forces relax and compressed interiors rebound. Repeated compression creates internal friction, converting orbital energy into heat, warming interiors. Over time, heating raises internal temperatures, maintaining liquid water layers despite frigid external environments. The process matches the mechanism heating Jupiter's moon, Europa, where tidal heating keeps subsurface water liquid despite extreme distance and frigid surfaces. Rogues with moons create numerous small ocean worlds maintained liquid by tidal heating, potentially supporting microbial subsurface life despite absent stellar radiation. Rogue planets preserve isotopic signatures from formation, chemical fingerprints revealing where and when the rogues originated within their parent star systems. Different stellar environments produce different isotopic ratios, variations in the relative abundance of different isotopes of the same element. A protoplanetary disk around a metal-rich star contains different isotope ratios than a disk around a metal-poor star, because the stellar nucleosynthesis that created the disk's material produced different mixtures of isotopes. When a rogue forms within such a disk and is subsequently ejected, it carries this isotopic signature with it into interstellar space. Over billions of years, the rogue wanders through the galaxy, but the isotopic composition of its materials remains unchanged, a permanent record of the environment where the rogue formed. Astronomers studying rogue composition can measure isotope ratios and use these measurements to infer properties of the star system where the rogue originated, even if that star system no longer exists or lies too distant to observe directly. The isotopic signatures can reveal information about the timing of the rogue's ejection, because certain radioactive isotopes decay at known rates, and the current abundance of decayed products relative to remaining parent isotopes reveals how much time has elapsed since the isotopic system was closed. These isotopic clocks allow rogues to be age-dated and their origins reconstructed from chemical evidence alone. Atmospheric hazes scatter infrared radiation efficiently, with suspended particles in rogue atmospheres absorbing and re-radiating thermal energy, rather than allowing it to escape freely into space. Complex organic molecules created by photochemical processes in the atmosphere or supplied by cosmic ray interactions can polymerize into larger structures forming aerosol particles. These particles scatter light and thermal radiation, disrupting the direct escape of radiation from the planetary surface. The scattering creates an insulating effect, preventing thermal radiation from the interior from radiating freely into space, and causing a modest greenhouse effect even without stellar heating. The hazes would appear as visible layers in the upper atmosphere if the rogue possessed sufficient internal illumination. But since rogues exist in complete darkness, the hazes would be invisible to external observation. The efficiency of the haze at scattering radiation depends on particle size and abundance, with denser hazes creating stronger insulation effects. Over billions of years, atmospheric chemistry might change and hazes might accumulate or dissipate, altering the degree of insulation the haze provides. The haze effect contributes to rogues' ability to retain internal heat, preventing rapid heat loss that might otherwise cool the rogue faster through direct radiation into space. Some rogues experienced planetary migration before ejection, movements of orbits caused by gravitational interactions with disk material or other planets during protoplanetary disk time. In young systems, planets form in inner disks where material abounds, then gradually migrate outward or inward as interactions alter orbits. Planets migrating significantly travel far into disks or back towards stars, altering composition and properties. Migration ceases once disks dissipate, leaving planets in orbits occupied when damping disappeared. Rogues ejected after migrating carry migration evidence in chemical compositions reflecting environments where they spent most time before ejection. Detecting evidence requires detailed chemical analysis revealing inconsistent abundances. Some rogues show migration evidence suggesting parent systems experienced complex histories with multiple planetary rearrangements before becoming unstable and ejecting rogues. Metallic cores generate persistent magnetic shielding, creating protective barriers around rogues that persist indefinitely as long as the interior remains hot enough to maintain liquid conducting material. The iron and nickel core of a rogue, being metallic and existing at extreme temperatures where electrons move freely between atoms, acts as an electrical conductor. When this conducting material moves due to convection or planetary rotation, electrical currents form that generate magnetic fields through dynamo processes. The magnetic field can persist for billions of years, sustained by the ongoing motion of the conducting fluid in the interior. The field extends outward into space, creating a magnetosphere many thousands of kilometers across where the magnetic force exceeds the pressure cutoff E of the interstellar medium. Within this magnetosphere, cosmic rays are deflected around the rogue rather than penetrating to the surface. The persistence of the metallic core's magnetic field over cosmic timescales means that rogues maintain this protection indefinitely, unlike some other planets whose magnetic fields decay and disappear over time. The strength of the field depends on the size and rotation rate of the metallic core, with larger, faster rotating cores generating stronger magnetic fields. Rogue planets drift through spiral arm structures, following paths that sometimes carry them through the grand spiral arms that give galaxies their distinctive appearance. The Milky Way contains several prominent spiral arms, density waves in the galactic disk where stars, gas and dust are more concentrated than in the regions between arms. Rogues ejected from stars within these spiral arms carry the velocity of their parent systems and drift through space following straight-line trajectories. A rogue's path might carry it through multiple spiral arms over billions of years, crossing the arms as the rogue's trajectory intersects the region of higher density. The passages through spiral arms expose the rogue to higher stellar densities and increase the probability of close encounters with other stars or objects. However, the spiral arms are not permanent structures. They rotate around the galactic center and gradually shift their positions. A rogue ejected from a star in one spiral arm might find that the arm has rotated away by the time millions of years have passed, leaving the rogue drifting through the lower density regions between arms. The interaction of rogue trajectories with galactic spiral structure creates complex patterns of migration through different galactic environments. Radiation processing creates complex surface chemistry, with cosmic rays and other high-energy particles initiating chemical reactions that transform surface minerals into more exotic compounds. Cosmic rays striking the rogue's surface penetrate the outer layers and ionize molecules in the rock and ice, creating free radicals and disrupting chemical bonds. The broken molecules can recombine into different configurations, creating compounds that would not form through ordinary thermal chemistry. Ultraviolet radiation from distant stars, though extremely faint over interstellar distances, can also contribute to radiation-driven chemistry. The combined effects of cosmic ray bombardment and weak ultraviolet illumination gradually alter the surface chemistry of the rogue, creating layers enriched in secondary minerals and unusual compounds unknown on planets with more moderate radiation environments. The process is slow, requiring millions of years to noticeably alter composition. But over billions of years of cosmic wandering, rogue surfaces can develop unique chemical signatures, reflecting their radiation history. Some of the complex organic molecules created by radiation processing might serve as chemical feedstocks for theoretical subsurface biochemistries. Complex carbon-based compounds created through radiation-driven reactions that might support unusual forms of life in subsurface environments. Ancient impact basins mark violent early histories. Craters recording collisions with asteroids or other objects when the rogue was younger and moved through more crowded regions of space. During the early history of a rogue, when it might still have been orbiting its parent star or had only recently been ejected, the rogue would have encountered more objects through collisions in the disk or in the early galactic environment. Impact events would have created craters, some enormous, and creating basins hundreds of kilometers across, others smaller and more numerous. The impacts would have altered the rogue's surface, melting rock at impact sites and potentially excavating material from the interior. As the rogue aged and drifted through progressively less crowded regions of space, impact events would have become rarer, allowing the ancient impact basins to persist as permanent features of the rogue's landscape. The distribution of impact basins across the rogue's surface reveals information about the impact history, with older rogues typically showing more impact scarring than younger ones. Some basins might preserve evidence of the impacting objects, ejector patterns, or material samples embedded in the basin walls, revealing the composition of the bodies that collided with the rogue. Some rogues host stratified atmospheric layers with distinct chemical compositions and temperature gradients, creating layered structures analogous to Earth's troposphere, stratosphere, and mesosphere. The densest atmosphere exists at the base, where pressure is highest and temperature is elevated by internal heat radiating from the rogue's surface. With increasing altitude, density decreases and temperature gradients establish distinct layers where chemical composition changes gradually. Ultraviolet radiation from distant background stars, though extremely faint, can trigger photochemical reactions in the upper atmosphere, creating ozone and other compounds enriched in high-altitude regions. The temperature inversions occurring where absorption of ultraviolet radiation heats the upper atmosphere, while the lower atmosphere remains cool. From surface radiation absorption creates stable layering that persists for extended periods. Atmospheric circulation patterns would be organized by the stratification, with distinct wind patterns in each layer responding to the temperature and pressure gradients. Over billions of years, as the rogue cools and internal heat flux decreases, the temperature gradient driving stratification would gradually weaken, eventually leading to mixing of the layers as thermal circulation patterns change. Geothermal gradients drive internal circulation currents, establishing patterns of convection that transport thermal energy from the rogue's interior outward toward the surface. The temperature at the base of the mantle might be thousands of degrees above the temperature at the surface, creating an enormous temperature gradient driving heat flow outward through conduction and convection. Convection occurs when a fluid heated from below becomes less dense, rises toward the surface, cools, becomes denser, and sinks back into the depths, establishing a circulation pattern that transports heat efficiently. The convection patterns in a rogue's mantle might be organized into columns or cells where hot material rises in some regions and cooler material descends in others. The rising material might reach the surface in regions where thermal vents release geothermal heat, while descending material cools in contact with the overlying crust. The circulation patterns would be influenced by the rogue's rotation, with faster rotation creating Coriolis effects that organize convection into distinct patterns. Over billions of years, as the rogue cools, the temperature gradient driving convection decreases, causing convection rates to slow and eventually diminish as the rogue approaches thermal equilibrium with its surroundings. Rogue planets occasionally pass near other wanderers, rare encounters between two rogues drifting through interstellar space, where gravitational interactions briefly alter both trajectories. The density of rogues in interstellar space is extremely low, but not zero, suggesting that over billions of years some rogues will inevitably pass close enough to other rogues for gravitational interactions to become significant. When two rogues pass nearby, their mutual gravity pulls them toward each other, altering both trajectories. If the encounter is sufficiently close, one rogue might capture a moon from the other, or transfer satellites between the two bodies. More distant encounters would produce only minor trajectory deflections, changing the rogue's velocities by small amounts. The probability of extremely close encounters approaches zero, but over cosmic timescales, the extremely long periods between ejection events and observation mean that even exceedingly rare events might occasionally occur. Such encounters would represent dramatic moments in otherwise placid cosmic journeys, brief interactions with another planetary body before returning to solitary wandering. The encounter might produce temporary tidal heating on both bodies, warming them through gravitational stretching as the two rogues pass each other. Primordial atmospheres evolve through photochemical processes, creating new compounds through reactions triggered by ultraviolet radiation and cosmic rays over billions of years. A rogue's original atmosphere, inherited from its formation in a protoplanetary disk, contains certain baseline compositions of hydrogen, helium, water vapor, methane, and other compounds. Over time, ultraviolet radiation and cosmic rays break these molecules apart, creating free radicals and reactive fragments. The fragments recombine through various pathways, creating new compounds not present in the original atmosphere. Some reactions produce heavier molecules that can form aerosol particles, creating haze layers in the atmosphere. Other reactions create compounds that escape more easily than their parent molecules, altering the atmospheric composition over time. The diversity of possible reactions means that rogue atmospheres could evolve through thousands of different chemical pathways, depending on the initial composition and the intensity of radiation exposure. Over billions of years, a rogue's atmosphere could transform completely from its original composition to something entirely different. A metamorphosis driven entirely by radiation and chemistry operating in complete darkness. Captured dust forms tenuous ring systems, with interstellar dust accumulated by the rogue potentially establishing organized structures orbiting the planetary body. When a rogue accumulates dust from the interstellar medium, The dust particles don't distribute randomly around the rogue, but instead accumulate in orbital bands where gravitational dynamics permit stable configurations. The dust particles experience mutual collisions that gradually damp their random motions, causing them to settle into orbital configurations analogous to planetary rings. The ring systems would be tenuous and difficult to detect, composed of microscopic particles spread across vast regions, rather than densely packed structures. The rings would be gradually depleted over time as particles spiral inward due to atmospheric drag or escape outward due to gravitational interactions with captured moons. The composition of the dust rings would reflect the composition of the interstellar dust encountered, typically silicates and carbon-based materials with admixtures of ice and frozen volatiles. The presence of ring systems distinguishes rogues with accumulated dust from those that remain pristine, creating diversity in rogue planetary structures. Some rogues maintain hydrostatic equilibrium shapes, with spherical or slightly oblate forms reflecting the balance between gravitational compression and rotational centrifugal forces. Gravity pulls a rogue's material inward, attempting to compress it into the smallest possible volume, a perfect sphere. Rotation creates centrifugal effects that oppose gravity, pushing material outward, especially at the equator. The equilibrium between these competing forces determines the rogue's final shape. Most rogues are nearly spherical because their rotation rates are relatively modest and gravity remains the dominant force. Faster rotating rogues develop equatorial bulges where the centrifugal effect becomes more significant. The exact shape depends on the rogue's mass, rotation rate, and internal density distribution. Over billions of years, tidal interactions with captured moons might gradually alter a rogue's rotation rate, slowly changing the degree of equatorial bulge. Some very ancient rogues might have slowed to extremely slow rotation rates, returning to nearly perfect spheres after originally being more oblate when rotation rates were higher. Interstellar medium interactions strip outer atmospheres, with the sparse gas and dust filling interstellar space, slowly removing atmospheric particles through collisions and gravitational focusing effects. The interstellar medium, though extremely low density compared to planetary atmospheres, still contains atoms and molecules that can collide with a rogue's atmosphere. These collisions transfer momentum, slowly accelerating atmospheric particles and lifting some above escape velocity. Additionally, gravitational focusing effects concentrate interstellar particles on the rogue's front hemisphere as it travels through space, creating asymmetric atmospheric erosion where the trailing hemisphere loses less material. The stripping process is extremely slow, removing only tiny fractions of the atmosphere over millions of years, but over billions of years the cumulative effect becomes significant. Older rogues might have lost substantial fractions of their original atmospheres, gradually becoming stripped of volatiles, while heavier elements remain behind. The process preferentially removes lighter elements like hydrogen and helium, while retaining heavier elements like oxygen and nitrogen, gradually shifting atmospheric composition toward heavier elements. Thermal inversions create stable atmospheric structures, with regions where temperature increases with altitude rather than decreasing, a configuration that traps convection and stabilizes the atmosphere against mixing. In Earth's stratosphere, Ozone absorption of ultraviolet radiation heats the upper atmosphere, creating a temperature inversion where temperature increases with altitude. On a rogue planet, similar processes might create temperature inversions where ultraviolet radiation from distant background stars heats certain atmospheric layers. The heated layer becomes denser than the layers above it, despite containing different chemical composition, creating a stable configuration resistant to mixing. Convection driven by heating from below cannot penetrate through the inversion layer, instead being reflected downward and confined to the lower atmosphere. The stability created by thermal inversions might persist for billions of years as long as the ultraviolet radiation source remains. The inversion layers would influence where various chemical compounds accumulate, with some compounds concentrated below the inversion layer and others enriched above it, creating distinct chemical stratification. Rogue planets experience gravitational perturbations from dark matter, the invisible matter comprising most of the Milky Way's mass, subtly altering rogue trajectories through gravitational effects. Dark matter exists throughout the galaxy in the form of the dark matter halo surrounding the visible disk. The distribution of dark matter is uneven, with denser concentrations in some regions and lower densities in others. As a rogue travels through the galaxy, it experiences gravitational forces not only from visible stars and gas, but also from the surrounding dark matter. The gravitational effects of dark matter are subtle, typically causing deflections orders of magnitude smaller than those from nearby stars. But over billions of years of cosmic wandering, the accumulated effects become measurable. Astronomers studying rogue trajectories and attempting to trace them backward to their origins must account for dark matter effects to achieve complete accuracy. The dark matter perturbations create uncertainty in rogue origin predictions, as the exact trajectory depends on knowledge of dark matter distribution throughout the galaxy. Some rogues might pass through regions of higher dark matter density where gravitational effects are more pronounced, experiencing larger trajectory deflections than rogues passing through lower density regions. Ancient volcanic features mark extinct geological activity, relics of epochs when a rogue's interior remained hot enough to drive magmatism and create volcanic landforms at the surface. Extinct volcanic features might include shield volcanoes, broad, low-profile mountains created by the eruption of low-viscosity lava that flowed great distances before solidifying. Caldera structures, the collapse features created when magma chambers empty, might persist as large circular depressions on the rogue's surface. Volcanic ridges and fissures marking locations where lava erupted from deep cracks would create linear features across the terrain. Lava tubes, tunnel-like structures created when flowing lava cooled on the surface while remaining fluid in the interior, might create networks of underground passages. Over billions of years, impact cratering and surface weathering would gradually erase the fine details of these volcanic features, but large structures like calderas might persist recognizably for the age of the galaxy itself. The distribution of volcanic features provides evidence about which regions of the rogue experienced the most intense magmatism and thus the highest internal heat flux. The ages of different volcanic features can be estimated from crater density analysis, with older surfaces showing more accumulated attenuated impacts than younger ones. Atmosphere through gravitational means alone, retaining thick envelopes of hydrogen and helium that insulate interior heat and maintain elevated temperatures despite the cold void surrounding them. This retention mechanism means that massive rogue planets function as isolated thermal systems where atmospheric pressure prevents volatile escape and interior warmth persists for billions of years. Sub-brown dwarf rogues challenge conventional classification systems, occupying a nebulous region between the smallest stars and the largest planets, where traditional boundaries blur into uncertainty. These massive wanderers, possessing sufficient mass that deuterium fusion occurred briefly during their formation, exist at the threshold where stellar and planetary definitions diverge. Astronomers debate whether objects fusing deuterium belong to the planetary category or represent the lowest mass stars, a distinction meaningful only in how we choose to organize our understanding of cosmic objects. A rogue with 13 Jupiter masses could theoretically have undergone deuterium burning during youth, creating an object that bridges both categories. The classification difficulty arises because the C objects share characteristics with both planets and stars, possessing planetary formation histories while exhibiting stellar fusion processes. As these rogues age and cool, the distinction becomes less meaningful, mere semantic boundaries drawn by human convention rather than reflecting fundamental differences. The objects themselves exist indifferent to our taxonomies, cold wanderers pursuing their silent trajectories through space, regardless of how we choose to categorize them. Atmospheric convection patterns emerge without stellar heating, driven entirely by the temperature gradient between the rogue's hot interior and the frigid interstellar environment surrounding it. Warm air heated by internal geothermal processes rises through the lower atmosphere, while cooler air sinks in a perpetual circulation pattern sustained by the temperature differential. The convection organizes into cell structures where rising plumes create regions of higher pressure in the upper atmosphere, while descending air creates low-pressure zones at the surface. These circulation patterns influence where clouds form, where precipitation might occur if water vapor exists, and how atmospheric chemistry distributes across latitudes. The convection strength depends directly on interior temperature and how quickly heat flows towards the surface, with rapidly cooling rogues showing weaker circulation than younger, hotter objects. Over billions of years, as rogues gradually cool and the temperature gradient decreases, atmospheric circulation slows and eventually approaches stasis as thermal driving diminishes. The patterns represent one of the few dynamic processes possible on worlds devoid of stellar heating. Silent exchanges of heat between interior and space that continue long after nuclear fusion and stellar heating have faded from memory. Rogue planets preserve clues about planetary system formation through their trajectories and compositions, each object carrying evidence of the system that ejected it into the void. The velocity and direction of a rogue can be extrapolated backward through space to determine where the object originated, revealing which star systems contributed to the wandering population. Chemical abundances in the rogue's atmosphere and surface rocks reflect the composition of the protoplanetary disk where it formed, information preserved through billions of years of isolation, Isotopic ratios of various elements provide fingerprints linking rogues to specific stellar populations and formation epochs, allowing reconstruction of when various rogues were ejected. Orbital history leaves imprints in the rogue's chemical structure, with rogues that migrated extensively showing different compositions than those that formed and were immediately ejected. The collection of ejected rogues essentially represents a sampling of planetary materials from throughout the galaxy, a distributed archive of planetary chemistry accessible to astronomers studying exoplanet formation. Each rogue carries a story encoded in its physical properties, a narrative of system formation, planetary interactions, chaos, and eventual expulsion inscribed in rock and ice. Some rogues travel in loose gravitational associations with other rogue planets, pairs or small groups drifting together through space despite the enormous distances separating most wanderers. Two rogues ejected from the same system might be captured into a binary configuration where mutual gravity keeps them in orbital relationship despite the weakness of their gravitational attraction across interstellar distances. The orbital periods of such systems could span thousands or millions of years, with rogues approaching and retreating in slow dances covering astronomical units of space. These binaries would eventually decay over cosmic timescales as interstellar gas and dust gradually extract orbital energy, causing the rogues to spiral closer until they collide or pass within each other's sphere of influence. Other loose associations might involve rogues that happen to move through space on nearly parallel trajectories, remaining in proximity for millions of years before gradual orbital divergence carries them apart permanently. These associations reveal that even the coldest, most isolated wanderers occasionally maintain gravitational connections with others of their kind, brief cosmic partnerships in otherwise solitary journeys. Ancient craters reveal bombardment, histories stretched across the rogue's existence, permanent records of collisions with asteroids, dust grains, and other objects accumulated during billions of years of cosmic wandering. A young rogue might have accumulated significant impacts while drifting through the crowded environment of its birth system, or while passing through the galactic disk where stellar densities remain higher. The distribution of impacts across the rogue's surface shows bombardment patterns, with older surfaces typically displaying more accumulated craters than younger ones. Large impact basins from early in the rogue's history might be partially obscured by younger impacts or erased by geological processes, while recent impacts appear as sharp-edged craters with minimal erosion. The abundance of small impacts vastly exceeds large ones, following power law distributions common to impact populations throughout the solar system. Each crater represents a moment of violent collision, a brief encounter between the rogue and another object traveling through the void, moments of drama interrupting the rogue's otherwise peaceful wandering. Thermal emission peaks in specific infrared bands determined by the rogue's surface temperature and atmospheric composition, creating signatures detectable by sensitive infrared telescopes even though visible light remains impossible. A rogue with surface temperatures around 300 Kelvin would emit primarily in the near-infrared, with emission peaks at wavelengths around 10 micrometers, where objects at that temperature radiate most strongly. Cooler rogues with surface temperatures near 100 Kelvin emit at longer infrared wavelengths, requiring space telescopes sensitive to far infrared radiation to detect. Atmospheric components absorb and re-emit at characteristic wavelengths, creating absorption features in the thermal spectrum that reveal chemical composition. A rogue with methane-rich atmosphere would show distinctive absorption bands at wavelengths where methane strongly absorbs radiation. These thermal signatures provide the primary method for detecting and characterizing rogues, transforming invisible wanderers into bright beacons in infrared surveys. The specific wavelengths carrying the thermal information encode details about surface temperature, atmospheric chemistry, and internal heat flux. Information extracted by careful analysis of the infrared spectra. Rogue planets cross through star-forming regions, passing through the spectacular nebulae where new stars and planets continue to form despite the rogue's own ancient isolation. The encounter between a lonely wanderer and an active star-forming region creates opportunities for gravitational interactions with young planetary systems still embedded in protoplanetary disks. A rogue passing nearby might capture a moon from a young system, add to its collection of gravitational-bound objects, or trigger instabilities that affect ongoing planetary formation in the region. The passage would introduce an additional gravitational perturbation into the delicate dynamics of systems still settling into final configurations. Some young planets might be accelerated or decelerated by the passing rogue, altering their orbital periods and potentially affecting long-term system stability. The encounter would be brief on cosmic timescales, but potentially significant for the young systems involved, a fleeting interaction between old and young worlds. Exotic chemistry occurs in high-pressure atmospheres where conditions exceed those achievable in any terrestrial laboratory, creating compounds and phases unknown in normal planetary environments. The pressure at the base of a rogue's atmosphere could exceed thousands of atmospheres despite the frigid external temperature. Compression sufficient to alter chemistry fundamentally. Hydrogen and helium under such compression behave as exotic fluids with unusual properties, transitioning through phases neither liquid nor gas in their conventional sense. Carbon atoms subjected to extreme pressure might form arrangements unknown in normal matter, potentially creating extended networks of bonded atoms with unique chemical properties. Nitrogen molecules compress into exotic phases at the pressures existing in deep rogue atmospheres, creating conditions that might support unusual nitrogen chemistry. Water beneath extreme pressure and cold temperature creates exotic ice phases, solid structures with properties radically different from normal ice. These high-pressure chemistries represent natural experiments in extreme chemistry, laboratories maintained by the rogue's own gravitational compression. Some rogues formed through gravitational fragmentation of collapsing molecular clouds, a formation mechanism distinct from planetary ejection and more akin to star formation processes. When massive clouds of gas and dust collapse under their own gravity, the collapsing material sometimes fragments into multiple clumps if rotation or magnetic fields introduce perturbations. The fragmentation can produce objects ranging from stellar masses down to planetary masses, with the smallest fragments becoming rogue planets rather than stars. This formation pathway means some rogues lack the developmental history of planetary systems, instead forming in isolation from the beginning. Such rogues would possess chemical compositions reflecting the materials of their birth cloud rather than the compositions of protoplanetary disks. Isolated formation explains some rogues that appear to have no connection to nearby star systems, objects that formed locally from their immediate environment rather than being ejected from distant systems. The distinction between ejected and fragmentation-formed rogues remains a topic of active investigation, with compositional and kinematic studies attempting to determine which rogues formed through which process. Mantle convection continues in geologically active rogues, driving large-scale circulation patterns within the rogue's interior that transport heat and gradually alter internal structure. The temperature gradient between the rogue's hot interior and relatively cooler outer mantle creates pressure differences driving convection, a circulation pattern that persists as long as internal temperature exceeds the surrounding environment. Rising plumes of warm mantle material carry heat toward the surface, while descending plumes of cooler material move inward, establishing patterns that repeat over millions of years. The convection rate depends on the vigor of the temperature gradient and the viscosity of mantle rock at the prevailing temperature and pressure, with hotter younger rogues showing faster convection than older cooling rogues. The circulation patterns transport dissolved elements and chemical compounds, gradually mixing the mantle over geologic time and homogenizing complexity. Position. As rogues age, the declining temperature gradient slows convection, eventually reducing it to near stasis as the internal heat source gradually diminishes through radiative escape and cooling. Rogue planets accumulate micrometeorite impacts over time, collecting microscopic dust and grains from the interstellar medium as they travel through space. The surfaces of rogues gradually collect layers of interstellar material, micrometers and millimeters of dust settling out of collisions with the rogue's atmosphere or direct impacts with the solid surface. The accumulated dust changes the surface reflectivity, darkening the rogue as layers of reddish interstellar dust collect. The composition of accumulated dust reveals the chemical environment the rogue passed through, with rogues traveling through different galactic regions accumulating different mineral compositions. Some dust contains complex organic compounds formed in other stars' outflows, enriching the rogue with prebiotic chemistry. Over billions of years, the accumulated dust layer might become sufficiently thick that it contributes measurably to the rogue's heat budget, insulating the interior slightly from the cold environment. The process represents a form of slow contamination, a gradual enrichment of the rogue's surface with materials from the broader cosmos. Captured objects orbit in chaotic, unstable patterns rather than settling into neat, predictable configurations, their motions governed by complex gravitational interactions within the rogue's gravitational field. A rogue that captures multiple moons or small asteroids creates a miniature system where the orbits of the captured objects interact gravitationally with each other and with the rogue. The complexity of the multi-body problem means that some initial configurations lead to stable long-term orbits, while others prove unstable, eventually resulting in collision, ejection, or merger of the captured bodies. Chaotic dynamics means that the exact trajectories become unpredictable over sufficiently long timescales, despite the deterministic nature of gravity. Sensitive dependence on initial conditions rendering the system's long-term evolution uncertain. Some captured objects might undergo orbital resonances where their orbital periods maintain mathematical relationships, creating patterns of periodically aligned positions. Others might spiral gradually inward or outward over millions of years, their orbits decaying or expanding due to tidal interactions and gravitational perturbations. Ancient magnetic fields recorded in crustal rocks provide evidence of past planetary magnetism. A record of the rogue's magnetic history preserved in the orientation of magnetic domains within the rock. When molten lava cools at the surface, magnetic minerals within the cooling material align themselves with the ambient magnetic field present at that moment. The aligned magnetic grains become locked in place as the rock solidifies, preserving a record of the field's direction and strength at the time of cooling. By studying the magnetic orientation of ancient lava flows erupted early in the rogue's history, scientists can determine the strength and configuration of the rogue's magnetic field in the past. Changes in the magnetic field strength recorded in successive lava flows reveal how the field evolved, whether it strengthened or weakened over geological epochs. Some ancient rogues show evidence of stronger magnetic fields in their youth, a pattern consistent with more vigorous mantle convection driving the dynamo process when internal heat was more abundant. Some rogues possess layered cloud structures where distinct layers of clouds or hazes form at different altitudes based on the temperature profile and atmospheric composition. The coldest layers in the upper atmosphere might contain different compounds than warmer layers closer to the surface, creating a stratification where each layer reflects different chemical compositions. Clouds of ammonia ice might form at one altitude, while methane ice clouds form at another, creating visible layering if external light illuminated the rogue. The density structure of the atmosphere creates natural boundaries where different materials preferentially exist as solids or gases, establishing the layers. Temperature inversions created by selective radiation absorption might stabilize layers against mixing, maintaining distinct chemical provinces in the upper atmosphere. Over billions of years, the changes in internal heat flux and atmospheric circulation patterns might gradually alter the altitude where particular compounds condense and freeze. Thermal contraction creates surface fracture networks as the rogue's surface cools and contracts. Stress patterns producing cracks radiating across the solid exterior. When cooling rock contracts, it shrinks slightly in all directions, but the contraction cannot occur uniformly if the rogue possesses a solid crust overlying a still warm interior. The crust cools faster than the interior, creating stress as the cooler outer layers shrink around the still warm interior. This differential cooling creates internal stresses that the rock relieves through fracturing, cracks propagating outward from high-stress zones. The fracture patterns form networks, often resembling polygonal patterns where the cracks intersect at approximately equal angles, a natural result of stress distribution in contracting materials. These surface fracture networks persist over billions of years, marking the slow cooling of the rogue's interior. The fractures might become conduits for underground flows of liquid materials, if any exist, or allow deeper portions of the interior to interact with the surface environment. Rogue planets pass through galactic plane oscillations, following paths that carry them alternately above and below the densest parts of the galactic disk, in cyclic patterns spanning tens of millions of years. The gravitational attraction of the dense stellar and gas population in the galactic plane pulls rogues toward the disk if they wander above it, while the gravity gradient of stars and gas creates a restoring force. The result resembles the motion of a ball rolling through a valley, oscillating back and forth as gravity repeatedly draws the rogue toward the plane and inertia carries it across toward the other side. A rogue ejected perpendicular to the disk might spend millions of years oscillating through these plane crossings, repeatedly passing through regions of high stellar density, where the probability of close encounters increases temporarily. The amplitude of these oscillations depends on the rogue's velocity perpendicular to the disk when ejected, with faster perpendicular velocities producing larger amplitude oscillations. Over the age of the galaxy, a single rogue might complete dozens of complete oscillations, repeatedly sampling the environment of high and low stellar density. Subsurface pressure maintains exotic material phases that cannot exist at surface conditions, regions where compression forces create states of matter foreign to normal planetary environments. Deep within a rogue's interior, the pressure from overlying weight reaches levels sufficient to force materials into unusual configurations. Hydrogen atoms experience compression sufficient to force electron clouds to overlap, creating degenerate matter where quantum mechanical effects become dominant. Iron, under extreme pressure, might assume crystal structures unknown at lower pressures, arrangements of atoms impossible under normal conditions that disappear if the pressure were reduced. The density of materials increases with depth, with the densest materials compressed into the innermost core, where pressure reaches its maximum. These exotic phases possess properties radically different from their equivalents at surface conditions, creating chemical and physical behaviors truly alien to terrestrial experience. The boundaries between these pressure-dependent phases occur at specific depths determined by the rogue's mass and density structure. Ancient water reservoirs persist in protected regions of some rogues. Liquid or solid water that accumulated during formation and remains preserved despite the surrounding frigid environment. Water incorporated into a rogue during its formation might remain protected in subsurface regions where geothermal heat prevents freezing. The combination of internal warmth and insulation provided by overlying rock layers could maintain liquid water in deep pockets despite surface temperatures far below water's normal freezing point. If a rogue possessed sufficient water and the right interior conditions, subsurface oceans might exist within its interior, vast reservoirs of liquid water sheltered from the cosmic vacuum. Such oceans would exist in complete darkness, never illuminated by stars, sustained by internal heat alone. If any microbial life evolved in such environments, it would represent a completely separate origin event, organisms that developed in isolation from Earth life and might possess entirely different biochemistry. The prospects for life in such deep oceans represent a frontier of astrobiology, the possibility of life in the absolute darkest depths of cosmic isolation. Some rogues experience temporary binary capture events when their paths bring them sufficiently close to other passing rogues that mutual gravity briefly creates a temporary binary system. The two rogues might orbit each other for days or weeks as they pass, their paths curving under mutual gravity before they move far enough apart that the gravitational attraction weakens to negligible levels. During the close approach, The rogues would experience tidal heating from the other's gravitational pull, stress on the rogue's interior creating brief moments of enhanced internal heating. The tidal forces might temporarily accelerate mantle convection, strengthen magnetic fields driven by interior dynamics, or trigger minor volcanic activity if sufficient heat accumulated. Once the rogues move up to the tidal heating ceases and the system returns to isolation, both rogues resuming solitary paths as if the encounter never occurred. Such encounters remain vanishingly rare, given the enormous distances between rogues, but over billions of years, even extremely improbable events become virtually certain to occur at least once. Radiation belts form around magnetized wanderers, regions where charged particles from cosmic rays become trapped by the magnetic field and spiral along magnetic field lines. A rogue with a strong magnetic field creates a magnetosphere extending thousands of kilometers into space, a region where the magnetic force exceeds the pressure of the interstellar medium. Cosmic ray particles striking the magnetosphere become deflected, with charged particles following spiral trajectories along magnetic field lines rather than penetrating directly to the surface. The trapped particles create radiation belts reminiscent of those surrounding magnetized planets in the solar system, energetic particles bouncing back and forth along field lines in patterns determined by magnetic geometry. The radiation belt else would emit radiation detectable in certain wavelengths, providing another observational signature of magnetized rogues. Over time, the radiation belts gradually lose particles through collisions with the thin interstellar medium, and gradual decay of the magnetic field driving the trapping process. But trapping continues as long as the magnetic field persists. Rogue planets influence local space environment chemistry, altering the composition of the interstellar gas and dust surrounding them through outgassing and surface interactions. Gases released from internal sources might escape the rogue's gravitational field into the surrounding space, creating a thin atmospheric envelope extending beyond the rogue's solid surface. Chemical reactions occur in this extended envelope, where rogue-derived materials interact with the ambient interstellar medium, creating secondary compounds not found in isolation. Some molecules created in this envelope might drift away, becoming dispersed throughout the surrounding cubic light-years of space. The rogue becomes a center of localized chemical perturbation, a point source creating compositional variations in its otherwise relatively uniform interstellar medium. The degree of chemical influence depends on the rogue's outgassing rate, its temperature, and the flux of cosmic radiation and solar wind-like flows from distant stars. Ancient rogues gradually ceased influencing their environment. As their outgassing diminished, their chemical impact fading along with their internal heat. Deuterium burning occurs briefly in massive rogues, a nuclear fusion process consuming deuterium atoms during the rogue's formation before the internal temperature declined below the threshold for fusion. Deuterium, a heavy isotope of hydrogen with 1 proton and 1 neutron, fuses at lower temperatures than normal hydrogen, initiating fusion reactions at about 13 Jupiter masses. A newly formed rogue possessing this mass would experience internal temperatures and pressures sufficient for deuterium nuclei to collide and fuse, producing helium and releasing energy in the process. The energy release would briefly warm the rogue's interior, contributing to the internal heat budget. However, the deuterium fuel exists in limited abundance, only a tiny fraction of the total hydrogen in the rogue. Once the deuterium becomes depleted, the fusion reactions cease permanently, leaving the rogue to cool through radiative processes alone. The brief fusion phase might last only a few million years before deuterium exhaustion ends the reaction, a fleeting moment of self-luminosity in the rogue's vast cosmic existence. Ancient accretion disks left compositional signatures within the rogue, layered evidence of the materials that accumulated during formation and the chemical processes that occurred during the accretion phase. A rogue's interior might preserve concentric shells reflecting different stages of formation, with inner layers showing compositions accumulated early in the formation process, and outer layers reflecting later accretion. The chemical differences between these layers reveal how the composition of the accreting material changed as the rogue grew, whether particular elements preferentially accumulated at certain stages. Isotopic variations between layers provide clues about the temperature and pressure conditions during various growth stages, information encoded in the frozen isotopic records. Some layers might contain evidence of differentiation, chemical separation driven by gravity that moved denser elements toward the center. The internal structure represents a record of the rogue's growth and chemical evolution, a geological history written in layers of rock and compressed material. Some rogues rotate with extreme obliquities, their rotation axes tilted dramatically relative to their orbital planes, as if a cosmic collision knocked them on their sides. A large impact early in the rogue's history could have transferred enough angular momentum to tilt the rotation axis dramatically, creating a rogue that spins on a pole, oriented nearly perpendicular to its direction of motion. Such extreme obliquities would create unusual atmospheric circulation patterns, where the poles receive different thermal radiation than the equator, compared to planets with normal rotation axes. A rogue tilted so extremely that it rotates on its side experiences extreme seasonal effects if it orbits a star, though rogues possess no stars, so this effect applies only to potential satellites. The cause of extreme obliquities in some rogues remains uncertain, possibly indicating giant collisions during formation or gravitational interactions with other objects in the parent system before ejection. The persistence of these extreme tilts across billions of years suggests they represent stable configurations, unlikely to be significantly altered by subsequent interactions. Cryogenic temperatures preserve volatile compounds that would otherwise evaporate or decompose, creating a natural deep freeze where fragile materials remain intact indefinitely. The frigid surfaces and atmospheres of rogues create conditions where carbon monoxide, methane, ammonia, and more complex organic molecules remain solid or liquid without degradation. Compounds that would rapidly decompose at warmer temperatures persist indefinitely at rogue temperatures, frozen in place against chemical change. The preservation of organic compounds in such excellent condition might allow future missions to sample these molecules directly, recovering materials that reveal the chemical conditions in the rogue's parent system. Complex prebiotic organic compounds might accumulate on rogue surfaces over billions of years, building up from cosmic ray chemistry and the rogue's own outgassing, creating libraries of organic chemistry. The rogue becomes a natural archive preserving the chemical state of its formation environment, a time capsule maintaining molecular integrity across the age of the galaxy. Rogue planets test theories of planetary formation by providing real-world examples of worlds formed and evolved under conditions radically different from those in our solar system. Traditional planetary formation theory developed by studying planets orbiting stars, with models built on the assumption that stellar gravity dominates planetary orbits. Rogues ejected from their parent systems reveal that the universe contains other formation mechanisms and evolutionary pathways beyond those originally imagined. The existence of Earth-mass rogues challenges models that predict planetary formation should produce primarily large planets like Jupiter. The abundance of rogues provides statistical tests of formation models, allowing comparison between predicted and observed populations. Some formation simulations fail to produce sufficient rogues, suggesting that current models incompletely capture the processes responsible for planetary ejection. The continued discovery of new rogues provides increasingly detailed information about planetary populations, refining theories through real observations of actual objects. Atmospheric circulation transports heat from the rogue's interior pole to equator through poleward flow, distributing thermal energy across the surface and reducing temperature extremes between illuminated and shadowed hemispheres. Without stellar heating, the rogue's heat distribution depends entirely on internal geothermal heat and the efficiency of atmospheric circulation in transporting that heat. A global circulation pattern would develop where warm air rises at equatorial latitudes and flows toward poles in the upper atmosphere, sinking at the poles and returning to the equator near the surface. The circulation efficiency depends on the rogue's rotation rate and internal heat flux, with faster rotation producing stronger latitudinal circulation patterns. Some of the internal heat would escape at all latitudes, but concentrated polar cooling would occur without effective poleward heat transport. The circulation patterns might remain remarkably stable over billions of years, driven by the same internal heat sources that sustained them for geological ages. Ancient seas froze solid on cooling water worlds. If early rogues possessed sufficient water to form global oceans, and initially hot enough to maintain liquid water, those seas would have gradually frozen as the rogue cooled. The sequence of freezing would progress from the poles inward, ice sheets expanding gradually towards the equator as the rogue's internal heat declined and equilibrium surface temperatures dropped. The last liquid water would persist longest in the deepest ocean basins, where pressure slightly elevated the freezing point. Pockets of liquid persisting beneath kilometers of ice as the oceans froze from top and bottom simultaneously. Eventually, over millions of years, the entire water inventory would crystallize into solid ice, massive glaciers kilometers thick, covering the rogue's entire surface. Layered ice structures would preserve evidence of the freezing process, different ice phases forming at different temperatures as the rogue gradually cooled. The final state would be a completely frozen ball of ice and rock, a dead water world bearing testimony to its warmer past in the crystalline structures of its entombed oceans. Some rogues harbor the potential for unknown phenomena not yet predicted by theory or observed directly, possibilities existing at the intersection of extreme conditions that human experience does not readily sample. The combination of extreme cold, High internal pressure, unusual atmospheric chemistry, and isolation from stellar inputs might create situations where unexpected processes occur. Materials behave unpredictably under the combination of pressure and temperature existing deep within rogues, potentially creating chemical reactions or physical phenomena unknown to laboratory science. The isolation from stellar radiation removes certain energy sources available on star-orbiting planets, potentially allowing processes impossible in lit environments. Complex chemistry occurring over billions of years in the cold darkness might create compounds or organize matter in ways not anticipated by current chemical models. The possibility remains that future observations of rogues will reveal surprises, phenomena that force revision of our understanding of how the universe actually operates under the most extreme conditions it creates. The search continues for these silent wanderers, each new discovery bringing humanity closer to understanding the true nature of planetary distribution throughout the cosmos. Astronomical surveys grow more sensitive with advancing technology, revealing ever fainter and smaller rogue planets, expanding the census of these solitary worlds. Future missions like the Nancy Grace Roman Space Telescope promise to revolutionize rogue planet science, detecting hundreds or thousands of new objects and dramatically increasing the statistical understanding of rogue populations. Each new rogue discovered adds information about planetary formation mechanisms, system evolution, and the ultimate fate of worlds scattered from their birth systems. The rogues continue their quiet journeys through the darkness, indifferent to human observation, but increasingly subject to scientific scrutiny. The universe contains countless worlds beyond the reach of visible starlight, a silent multitude drifting through the void, each one a complete planetary body with its own history and destiny. And yet, in the profound isolation of these wanderers exists a strange beauty, a testament to the universe's fertility in creating worlds under circumstances we barely comprehend. The rogues carry within them the memory of the stars that created them, composed of stardust recycled through galaxies, each atom shaped by billions of years of cosmic history. They drift through the darkness following trajectories established by gravitational encounters long past, guided by laws as fundamental and eternal as the universe itself. Within their frozen crusts and cooling interiors persist the ongoing slow changes of geochemistry and physics, processes continuing long after the rogue's moment of ejection has receded into distant memory. The rogues may never harbor life or consciousness to appreciate their own existence, yet they persist as perfect examples of the universe's capacity to create complexity in isolation, order emerging from chaos, worlds existing complete unto themselves, regardless of whether any observer bears witness. If you have enjoyed this quiet exploration of the galaxy's loneliest worlds, I invite you to linger with the mystery. Consider the vast numbers of rogues drifting through the space between stars, countless silent voyages on journeys begun millions of years ago. Let the scale of this reality settle into your awareness, the realization that most planets in the universe exist in complete darkness without stars, most worlds untouched by any light from their home systems. For now, allow yourself to drift with these wanderers through the cool depths of space, released from the urgencies of illuminated worlds, settling into the peaceful isolation these journeys represent. Rest well, knowing the universe continues its vast work regardless of our observation, creating and scattering worlds across the emptiness in patterns we are only beginning to understand. Sleep now in the knowledge that somewhere out there, a rogue planet continues its eternal journey through the dark, unobserved and unimpeded, true to its solitary nature.